is done in PyTorch is to set the device variable. Now really you could set this to any variable you want, but you're going to see it used as device quite often. So CUDA if torch.CUDA is available, else CPU. So all this is going to say, and we'll see where we use the device variable later on, is set the device to use CUDA if it's available, so it is, so true. If it's not available, if we don't have access to a GPU that PyTorch can use, just default to the CPU. So with that being said, there's one more thing. You can also count the number of GPUs. So this won't really apply to us for now because we're just going to stick with using one GPU, but as you upgrade your PyTorch experiments and machine learning experiments, you might have access to more than one GPU. So you can also count the devices here. We have access to one GPU, which is this here. So the reason why you might want to count the number of devices is because if you're running huge models on large data sets, you might want to run one model on a certain GPU, another model on another GPU, and so on and so on. But final thing before we finish this video is if we go PyTorch device agnostic code, CUDA semantics, there's a little section in here called best practices. This is basically what we just covered there, is setting the device argument. Now this is using the arg pass, but so yeah, there we go. args.device, torch.device CUDA, args.device, torch.device CPU. So this is one way to set it from the Python arguments when you're running scripts, but we're using the version of running it through a notebook. So check this out. I'll just link this here, device agnostic code. It's okay if you're not sure of what's going on here. We're going to cover it a little bit more later on throughout the course, but I'm going to write here. For PyTorch, since it's capable of running compute on the GPU or CPU, it's best practice to set up device agnostic code. E.g., run on GPU if available, else default to CPU. So check out the best practices for using CUDA, which is namely setting up device agnostic code. And let's in the next video see what I mean about setting our PyTorch tensors and objects to the target device. Welcome back. In the last video, we checked out a few different options for getting a GPU and then getting PyTorch to run on the GPU. And for now, we're using Google Colab, which is the easiest way to get set up because it gives us free access to a GPU, faster ones if you set up with Colab Pro, and it comes with PyTorch automatically set up to use the GPU if it's available. So now, let's see how we can actually use the GPU. So to do so, we'll look at putting tensors and models on the GPU. So the reason we want our tensors / models on the GPU is because using a GPU results in faster computations. And if we're getting our machine learning models to find patterns in numbers, GPUs are great at doing numerical calculations. And the numerical calculations we're going to be doing are tensor operations like we saw above. So the tensor operations, well, we've covered a lot. Somewhere here, tensor operations, there we go. Manipulating tensors, tensor operations. So if we can run these computations faster, we can discover patterns in our data faster, we can do more experiments, and we can work towards finding the best possible model for whatever problem that we're working on. So let's see. We'll create a tensor, as usual. Create a tensor. Now the default is on the CPU. So tensor equals torch.tensor, and we'll just make it a nice simple one. 1, 2, 3. And let's write here, tensor not on GPU. We'll print out tensor, and this is where we can use, we saw this parameter before, device. Can we pass it in here? Device equals CPU. Let's see what this comes out with. There we go. So if we print it out, tensor 1, 2, 3 is on the CPU. But even if we got rid of that device parameter, by default, it's going to be on the CPU. Wonderful. So now, PyTorch makes it quite easy to move things to, and I'm saying to for a reason, to the GPU, or to, even better, the target device. So if the GPU is available, we use CUDA. If it's not, it uses CPU. This is why we set up the device variable. So let's see. Move tensor to GPU. If available, tensor on GPU equals tensor.to device. Now let's have a look at this. Tensor on GPU. So this is going to shift the tensor that we created up here to the target device. Wonderful, look at that. So now our tensor 1, 2, 3 is on device CUDA 0. Now this is the index of the GPU that we're using. Because we only have one, it's going to be at index 0. So later on, when you start to do bigger experiments and work with multiple GPUs, you might have different tensors that are stored on different GPUs. But for now, we're just sticking with one GPU, keeping it nice and simple. And so you might have a case where you want to move, actually, the reason why we set up device agnostic code is, again, this code would work if we run this, regardless if we had, so it won't error out, but regardless if we had a GPU or not, this code will work. So whatever device we have access to, whether it's only a CPU or whether it's a GPU, this tensor will move to whatever target device. But since we have a GPU available, it goes there. You'll see this a lot. This to method moves tensors, and it can be also used for models. We're going to see that later on. So just keep to device in mind. And then you might want to, for some computations, such as using NumPy, NumPy only works with the CPU. So you might want to move tensors back to the CPU. Moving tensors back to the CPU. So can you guess how we might do that? It's okay if you don't know. We haven't covered a lot of things, but I'm going to challenge you anyway, because that's the fun part of thinking about something. So let's see how we can do it. Let's write down if tensor is on GPU, can't transform it to NumPy. So let's see what happens if we take our tensor on the GPU and try to go NumPy. What happens? Well, we get an error. So this is another huge error. Remember the top 3 errors in deep learning or PyTorch? There's lots of them, but number 1, shape errors. Number 2, data type issues. And with PyTorch, number 3 is device issues. So can't convert CUDA 0 device type tensor to NumPy. So NumPy doesn't work with the GPU. Use tensor.cpu to copy the tensor to host memory first. So if we call tensor.cpu, it's going to bring our target tensor back to the CPU, and then we should be able to use it with NumPy. So to fix the GPU tensor with NumPy issue, we can first set it to the CPU. So tensor back on CPU equals tensor on GPU dot CPU. We're just taking what this said here. That's the beautiful thing about PyTorch, is very helpful error messages. And then we're going to go NumPy. And then if we go tensor back on CPU, is this going to work? Let's have a look. Oh, of course it's not, because I typed it wrong. And I've typed it again, twice. Third time's a charm. There we go. Okay, so that works because we've put it back to the CPU first before calling NumPy. And then if we refer back to our tensor on the GPU, because we've reassociated this, again, we got typos galore, classic. Because we've reassigned tensor back on CPU, our tensor on GPU remains unchanged. So that's the 4 main things about working with PyTorch on the GPU. There are a few more tidbits, such as multiple GPUs, but now you've got the fundamentals. We're going to stick with using one GPU, and if you'd like to later on, once you've learned a bit more, research into multiple GPUs, well, as you might have guessed, PyTorch has functionality for that too. So have a go at getting access to a GPU using Colab, check to see if it's available, set up device agnostic code, create a few dummy tensors and just set them to different devices, see what happens if you change the device parameter, run a few errors by trying to do some NumPy calculations with tensors on the GPU, and then bring those tensors on the GPU back to NumPy and see what happens there. So I think we've reached the end of the fundamentals. We've covered a fair bit. Introduction to tensors, the min-max, a whole bunch of stuff inside the introduction to tensors, finding the positional min-max, reshaping, indexing, working with tensors and NumPy, reproducibility, using a GPU, and moving stuff back to the GPU. Far out. Now, you're probably wondering, Daniel, we've covered a whole bunch. What should I do to practice all this? Well, I'm glad you asked. Let's cover that in the next video. Welcome back, and you should be very proud of yourself right now. We've been through a lot, but we've covered a whole bunch of PyTorch fundamentals. These are going to be the building blocks that we use throughout the rest of the course. But before moving on to the next section, I'd encourage you to try out what you've learned through the exercises and extra curriculum. Now, I've set up a few exercises here based off everything that we've covered. If you go into learnpytouch.io, go to the section that we're currently on. This is going to be the case for every section, by the way, so just keep this in mind, is we're working on PyTorch fundamentals. Now, if you go to the PyTorch fundamentals notebook, this is going to refresh, but then if you scroll down to the table of contents, at the bottom of each one is going to be some exercises and extra curriculum. So these exercises here, such as documentation reading, because a lot, you've seen me refer to the PyTorch documentation for almost everything we've covered, a lot, but it's important to become familiar with that. So exercise number 1 is read some of the documentation. Exercise number 2 is create a random tensor with shape 7, 7. 3, perform a matrix multiplication on the tensor from 2 with another random tensor. So these exercises are all based off what we've covered here. So I'd encourage you to reference what we've covered in whichever notebook you choose. Could be this learnpytouch.io, could be going back through the one we've just coded together in the video. So I'm going to link this here, exercises. See exercises for this notebook here. So then, how should you approach these exercises? So one way would be to just read them here, and then in Colab, we'll go File, New Notebook, wait for the notebook to load. Then you could call this 00 PyTorch exercises or something like that. And then you could start off by importing Torch, and then away you go. For me, I'd probably set this up on one side of the screen, this one up on the other side of the screen, and then I just have the exercises here. So number 1, I'm not going to really write much code for that, but you could have documentation reading here. And then, so this encourages you to read through torch.tensor and go through there for 10 minutes or so. And then for the other ones, we've got create a random tensor with shape 7, 7. So we just comment that out. So torch, rand, 7, 7. And there we go. Some are as easy as that, some are a little bit more complex. As we go throughout the course, these exercises are going to get a little bit more in depth as we've learned more. But if you'd like an exercise template, you can come back to the GitHub. This is the home for all of the course materials. You can go into extras and then exercises. I've created templates for each of the exercises. So PyTorch fundamentals exercises. If you open this up, this is a template for all of the exercises. So you see there, create a random tensor with shape 7, 7. These are all just headings. And if you'd like to open this in Colab and work on it, how can you do that? Well, you can copy this link here, come to Google Colab, we'll go File, Open Notebook, GitHub. You can type in the link there, click Search. What's this going to do? Boom, PyTorch Fundamentals Exercises. So now you can go through all of the exercises. This will be the same for every module on the course and test your knowledge. Now, it is open book. You can use the notebook here, the ones that we've coded together, but I would encourage you to try to do these things on your own first. If you get stuck, you can always reference back. And then if you'd like to see an example solutions, you can go back to the extras. There's a solutions folder as well. And that's where the solutions live. So the fundamental exercise solutions, but again, I would encourage you to try these out, at least give them a go before having a look at the solutions. So just keep that in mind. At the end of every module, there's exercises and extra curriculum. The exercises will be code-based. The extracurriculum is usually like reading-based. So spend 1 hour going through the PyTorch basics tutorial. I'd recommend the quick start and tensor sections. And then finally, to learn more on how a tensor can represent data, watch the video, What's a Tensor, which we referred to throughout this. But massive effort on finishing the PyTorch fundamentals section. I'll see you in the next section. Friends, welcome back to the PyTorch workflow module. Now let's have a look at what we're going to get into. So this is a PyTorch workflow, and I say a, how cool was that animation? Because it's one of many. When you get into deep learning and machine learning, you'll find that there's a fair few ways to do things, but here's the rough outline of what we're going to do. We're going to get our data ready, turn it into tensors, because remember, a tensor can represent almost any kind of data. We're going to pick or build or pick a pre-trained model. We'll pick a loss function and optimizer. Don't worry if you don't know what they are. We're going to cover this. We're going to build a training loop, fit the model to make a prediction. So fit the model to the data that we have. We'll learn how to evaluate our models. We'll see how we can improve through experimentation. And we'll save and reload our trained model. So if you wanted to export your model from a notebook and use it somewhere else, this is what you want to be doing. And so where can you get help? Probably the most important thing is to follow along with the code. We'll be coding all of this together. Remember motto number 1, if in doubt, run the code. Try it for yourself. That's how I learn best, is I write code, I try it, I get it wrong, I try again, and keep going till I get it right. Read the doc string, because that's going to show you some documentation about the functions that we're using. So on a Mac, you can use Shift, Command, and Space in Google Colab, or if you're on a Windows PC, it might be Control here. If you're still stuck, try searching for it. You'll probably come across resources such as Stack Overflow or the PyTorch documentation. We've already seen this a whole bunch, and we're probably going to see it a lot more throughout this entire course, actually, because that's going to be the ground truth of everything PyTorch. Try again, and finally, if you're still stuck, ask a question. So the best place to ask a question will be at the PyTorch Deep Learning /Discussions tab, and then if we go to GitHub, that's just under here. So Mr. Debug, PyTorch Deep Learning, this is all the course materials. If we see here, this is your ground truth for the entire course. And then if you have a question, go to the discussions tab, new discussion, you can ask a question there. And don't forget to please put the video and the code that you're trying to run. That way we can reference what's going on and help you out there. And also, don't forget, there is the book version of the course. So learnpytorch.io. By the time you watch this video, it'll probably have all the chapters here. But here's what we're working through. This is what the videos are based on. All of this. We're going to go through all of this. How fun is that? But this is just reference material. So you can read this at your own time. We're going to focus on coding together. And speaking of coding, let's code. I'll see you over at Google Colab. Alrighty. Let's get hands-on with some code. I'm going to come over to colab.research.google.com. You may already have that bookmarked. And I'm going to start a new notebook. So we're going to do everything from scratch here. We'll let this load up. I'm just going to zoom in a little bit. Beautiful. And now I'm going to title this O1 PyTorch workflow. And I'm going to put the video ending on here so that you know that this notebook's from the video. Why is that? Because in the course resources, we have the original notebook here, which is what this video notebook's going to be based off. You can refer to this notebook as reference for what we're going to go through. It's got a lot of pictures and beautiful text annotations. We're going to be focused on the code in the videos. And then, of course, you've got the book version of the notebook as well, which is just a different formatted version of this exact same notebook. So I'm going to link both of these up here. So let's write in here, PyTorch workflow. And let's explore an example PyTorch end-to-end workflow. And then I'm going to put the resources. So ground truth notebook. We go here. And I'm also going to put the book version. Book version of notebook. And finally, ask a question, which will be where? at the discussions page. And then we'll go there. Beautiful. Let's turn this into Markdown. So let's get started. Let's just jump right in and start what we're covering. So this is the trend I want to start getting towards, is rather than spending a whole bunch of time going through keynotes and slides, I'd rather we just code together and then we explain different things as they need to be explained, because that's what you're going to be doing if you end up writing a lot of PyTorch, is you're going to be writing code and then looking things up as you go. So I'll get out of these extra tabs. I don't think we need them. Just these two will be the most important. So what we're covering, let's create a little dictionary so we can check this if we wanted to later on. So referring to our PyTorch workflows, at least the example one that we're going to go through, which is just here. So we're going to go through all 6 of these steps, maybe a little bit of each one, but just to see it going from this to this. That's what we're really focused on. And then we're going to go through the rest of the course, like really dig deep into all of these. So what we're covering, number 1 is data, preparing and loading. Number 2 is we're going to see how we can build a machine learning model in PyTorch or a deep learning model. And then we're going to see how we're going to fit our model to the data. So this is called training. So fit is another word. As I said, in machine learning, there's a lot of different names for similar things. Kind of confusing, but you'll pick it up with time. So we're going to, once we've trained a model, we're going to see how we can make predictions and evaluate those predictions. Evaluating a model, if you make predictions, it's often referred to as inference. I typically say making predictions, but inference is another very common term. And then we're going to look at how we can save and load a model. And then we're going to put it all together. So a little bit different from the visual version we have of the PyTorch workflow. So if we go back to here, I might zoom in a little. There we go. So we're going to focus on this one later on, improve through experimentation. We're just going to focus on the getting data ready, building a model, fitting the model, evaluating a model, save and reload. So we'll see this one more like in depth later on, but I'll hint at different things that you can do for this while we're working through this workflow. And so let's put that in here. And then if we wanted to refer to this later, we can just go what we're covering. Oh, this is going to connect, of course. Beautiful. So we can refer to this later on if we wanted to. And we're going to start by import torch. We're going to get PyTorch ready to go, import nn. So I'll write a note here. nn, we haven't seen this one before, but we're going to see a fair few things that we haven't seen, but that's okay. We'll explain it as we go. So nn contains all of PyTorch's building blocks for neural networks. And how would we learn more about torch.nn? Well, if we just go torch.nn, here's how I'd learn about it. PyTorch documentation. Beautiful. Look at all these. These are the basic building blocks for graphs. Now, when you see the word graph, it's referring to a computational graph, which is, in the case of neural networks, let's look up a photo of a neural network. Images. This is a graph. So if you start from here, you're going to go towards the right. There's going to be many different pictures, so yeah, this is a good one. Input layer. You have a hidden layer 2, output layer. So torch.nn comprises of a whole bunch of different layers. So you can see layers, layers, layers. And each one of these, you can see input layer, hidden layer 1, hidden layer 2. So it's our job as data scientists and machine learning engineers to combine these torch.nn building blocks to build things such as these. Now, it might not be exactly like this, but that's the beauty of PyTorch, is that you can combine these in almost any different way to build any kind of neural network you can imagine. And so let's keep going. That's torch.nn. We're going to get hands-on with it rather than just talk about it. And we're going to need matplotlib because what's our other motto? Our Data Explorer's motto is visualize, visualize, visualize. And let's check our PyTorch version. PyTorch version, torch.version. So this is just to show you, you'll need at least this version. So 1.10 plus CUDA 111. That means that we've got, CU stands for CUDA. That means we've got access to CUDA. We don't have a GPU on this runtime yet because we haven't gone to GPU. We might do that later. So if you have a version that's lower than this, say 1.8.0, you'll want PyTorch 1.10 at least. If you have a version higher than this, your code should still work. But that's about enough for this video. We've got our workflow ready to set up, our notebook, our video notebook. We've got the resources, we've got what we're covering, we've got our dependencies. Let's, in the next one, get started on 1, data, preparing and loading. I'll see you in the next video. Let's now get on to the first step of our PyTorch workflow, and that is data, preparing and loading. Now, I want to stress, data can be almost anything in machine learning. I mean, you could have an Excel spreadsheet, which is rows and columns, nice and formatted data. You could have images of any kind. You could have videos. I mean, YouTube has lots of data. You could have audio, like songs or podcasts. You could have even DNA these days. Patterns in DNA are starting to get discovered by machine learning. And then, of course, you could have text, like what we're writing here. And so what we're going to be focusing on throughout this entire course is the fact that machine learning is a game of 2 parts. So 1, get data into a numerical representation. 2, build a model to learn patterns in that numerical representation. Of course, there's more around it. Yes. I understand you can get as complex as you like, but these are the main 2 concepts. And machine learning, when I say machine learning, same goes for deep learning. You need some kind of, numerical, I like that word, numerical representation. Then you want to build a model to learn patterns in that numerical representation. And if you want, I've got a nice pretty picture that describes that. Machine learning, a game of 2 parts. Let's refer to our data. Remember, data can be almost anything. These are our inputs. So the first step that we want to do is create some form of numerical encoding in the form of tensors to represent these inputs. How this looks will be dependent on the data, depending on the numerical encoding you choose to use. Then we're going to build some sort of neural network to learn a representation, which is also referred to as patterns, features, or weights, within that numerical encoding. It's going to output that representation, and then we want to do something with that representation, such as in the case of this, we're doing image recognition, image classification. Is it a photo of ramen or spaghetti? Is this tweet spam or not spam? Is this audio file saying what it says here? Remember, I'm not going to say this because my audio assistant, that's also named this word here, is close by and I don't want it to go off. So this is our game of 2 parts. 1 here is convert our data into a numerical representation, and 2 here is build a model or use a pre-trained model to find patterns in that numerical representation. And so we've got a little stationary picture here. Turn data into numbers. Part 2, build a model to learn patterns in numbers. So with that being said, now let's create some data to showcase this. So to showcase this, let's create some known data using the linear regression formula. Now, if you're not sure what linear regression is or the formula is, let's have a look. Linear regression formula. This is how I'd find it. Okay, we have some fancy Greek letters here, but essentially we have y equals a function of x and b plus epsilon. Okay, well there we go. A linear regression line has the equation in the form of y equals a plus bx. Oh, I like this one better. This is nice and simple. We're going to start from as simple as possible and work up from there. So y equals a plus bx, where x is the explanatory variable and y is the dependent variable. The slope of the line is b. Now the slope is also known as the gradient, and a is the intercept. Oh, okay. The value of when x equals 0. Now, this is just text on a page. This is formula on a page. You know how I like to learn things. Let's code it out. So let's write it here. we'll use a linear regression formula to make a straight line with known parameters. I'm going to write this down because parameter is a common word that you're going to hear in machine learning as well. So a parameter is something that a model learns. So for our data set, if machine learning is a game of two parts, we're going to start with this. Number one is going to be done for us because we're going to start with a known representation, a known data set, and then we want our model to learn that representation. This is all just talk. Daniel, let's get into coding. Yes, you're right. Let's do it. So create known parameters. So I'm going to use a little bit different names to what that Google definition did. So weight is going to be 0.7 and bias is going to be 0.3. Now, weight and bias are another common two terms that you're going to hear in neural networks. So just keep that in mind. But for us, this is going to be the equivalent of our weight will be B and our bias will be A. But forget about this for the time being. Let's just focus on the code. So we know these numbers, but we want to build a model that is able to estimate these numbers. How? By looking at different examples. So let's create some data here. We're going to create a range of numbers. Start equals 0 and equals 1. We're going to create some numbers between 0 and 1, and they're going to have a gap. So the gap is going to be 0.02. Now we're going to create an x variable. Why is x a capital here? Well, it's because typically x in machine learning you'll find is a matrix or a tensor. And if we remember back to the fundamentals, a capital represents a matrix or a tensor, and a lowercase represents a vector. But in our case, it's going to be a little confusing because x is a vector, but later on, x will start to be a tensor and a matrix. So for now, we'll just keep the capital, not capital notation. We're going to create the formula here, which is, remember how I said our weight is in this case the B and our bias is the A. So we've got the same formula here. Y equals weight times x plus bias. Now let's have a look at these different numbers. So we'll view the first 10 of x and we'll view the first 10 of y. We'll have a look at the length of x and we'll have a look at the length of y. Wonderful. So we've got some values here. We've got 50 numbers of each. This is a little confusing. Let's just view the first 10 of x and y first, and then we can have a look at the lengths here. Length, x, length, y. So what we're going to be doing is building a model to learn some values, to look at the x values here, and learn what the associated y value is and the relationship between those. Of course, we know what the relationship is between x and y because we've coded this formula here. But you won't always know that in the wild. That is the whole premise of machine learning. This is our ideal output, and this is our input. The whole premise of machine learning is to learn a representation of the input and how it maps to the output. So here are our input numbers, and these are our output numbers. And we know that the parameters of the weight and bias are 0.7 and 0.3. We could have set these to whatever we want, by the way. I just like the numbers 7 and 3. You could set these to 0.9, whatever. The premise would be the same. So, and what I've just done here, I kind of just coded this without talking, but I just did torch a range and it starts at 0 and it ends at 1 and the step is 0.02. So there we go. 000 up by 0.02, 0.04, and I've unsqueezed it. So what does unsqueeze do? Removes the extra dimensions. Adds an extra dimension. Daniel, you're getting confused here. So if we remove that, we get no extra square bracket. But if we add unsqueeze, you'll see that we need this later on for when we're doing models. Wonderful. So let's just leave it at that. That's enough for this video. We've got some data to work with. Don't worry if this is a little bit confusing for now. We're going to keep coding on and see what we can do to build a model to infer patterns in this data. But right now, I want you to have a think. This is tensor data, but it's just numbers on a page. What might be a better way to this is a hint by the way, visualize it? What's our Data Explorer's motto? Let's have a look at that in the next video. Welcome back. In the last video, we created some numbers on a page using the linear regression formula with some known parameters. Now, there's a lot going on here, but that's all right. We're going to keep building upon what we've done and learn by doing. So in this video, we're going to cover one of the most important concepts in machine learning in general. So splitting data into training and test sets. One of the most important concepts in machine learning in general. Now, I know I've said this already a few times, one of the most important concepts, but truly, this is possibly, in terms of data, this is probably the number one thing that you need to be aware of. And if you've come from a little bit of a machine learning background, you probably well and truly know all about this, but we're going to recover it anyway. So let's jump in to some pretty pictures. Oh, look at that one. Speaking of pretty pictures, but that's not what we're focused on now. We're looking at the 3 data sets. And I've written down here possibly the most important concept in machine learning, because it definitely is from a data perspective. So the course materials. Imagine you're at university. So this is going to be the training set. And then you have the practice exam, which is the validation set. Then you have the final exam, which is the test set. And the goal of all of this is for generalization. So let's step back. So say you're trying to learn something at university or through this course. You might have all of the materials, which is your training set. So this is where our model learns patterns from. And then to practice what you've done, you might have a practice exam. So the mid-semester exam or something like that. Now, that's to see if you're learning the course materials well. So in the case of our model, we might tune our model on this practice exam. So we might find that on the validation set, our model doesn't do too well. And we adjust it a bit, and then we retrain it, and then it does better. Before finally, at the end of semester, the most important exam is your final exam. And this is to see if you've gone through the entire course materials and you've learned some things. Now you can adapt to unseen material. And that's a big point here. We're going to see this in practice, is that when the model learns something on the course materials, it never sees the validation set or the test set. So say we started with 100 data points. You might use 70 of those data points for the training material. You might use 15% of those data points, so 15 for the practice. And you might use 15 for the final exam. So this final exam is just like if you're at university learning something, is to see if, hey, have you learnt any skills from this material at all? Are you ready to go into the wild, into the quote-unquote real world? And so this final exam is to test your model's generalization. Because it's never seen this data, let's define generalization, is the ability for a machine learning model or a deep learning model to perform well on data it hasn't seen before, because that's our whole goal, right? We want to build a machine learning model on some training data that we can deploy in our application or production setting, and then more data comes in that it hasn't seen before, and it can make decisions based on that new data because of the patterns it's learned in the training set. So just keep this in mind, 3 data sets: training, validation, test. And if we jump in to the Learn PyTorch book, we've got split data. So we're going to create 3 sets, or in our case, we're only going to create 2, a training and a test. Why is that? Because you don't always need a validation set. There is often a use case for a validation set, but the main 2 that are always used is the training set and the testing set. And how much should you split? Well, usually for the training set, you'll have 60 to 80% of your data. If you do create a validation set, you'll have somewhere between 10 and 20. And if you do create a testing set, it's a similar split to the validation set. You'll have between 10 and 20%. So training, always. Testing, always. Validation, often, but not always. So with that being said, I'll let you refer to those materials if you want. But now let's create a training and test set with our data. So we saw before that we have 50 points. We have X and Y. We have 1-to-1 ratio. So one value of X relates to one value of Y. And we know that the split now for the training set is 60 to 80%, and the test set is 10 to 20%. So let's go with the upper bounds of each of these, 80% and 20%, which is a very common split actually, 80-20. So let's go create a train test split. And we're going to go train split. We'll create a number here so we can see how much. So we want an integer of 0.8, which is 80% of the length of X. What does that give us? Train split should be about 40 samples. Wonderful. So we're going to create 40 samples of X and 40 samples of Y. Our model will train on those 40 samples to predict what? The other 10 samples. So let's see this in practice. So X train, Y train equals X, and we're going to use indexing to get all of the samples up until the train split. That's what this colon does here. So, hey, X up until the train split, Y up until the train split, and then for the testing, oh, thanks for that autocorrect collab. I didn't actually need that one. X test, Y test equals X, and then we're going to get everything from the train split onwards. So the index onwards, that's what this notation means here. And Y from the train split onwards as well. Now, there are many different ways to create a train and test split. Ours is quite simple here, but that's because we're working with quite a simple data set. One of the most popular methods that I like is scikit-learn's train test split. We're going to see this one later on. It adds a little bit of randomness into splitting your data. But that's for another video, just to make you aware of it. So let's go length X train. We should have 40 training samples to how many testing samples? Length X test and length Y test. Wonderful, 40, 40, 10, 10, because we have training features, training labels, testing features, testing labels. So essentially what we've created here is now a training set. We've split our data. Training set could also be referred to as training split. Yet another example of where machine learning has different names for different things. So set, split, same thing. Training split, test split. This is what we've created. Remember, the validation set is used often, but not always, because our data set is quite simple. We're just sticking with the necessities, training and test. But keep this in mind. One of your biggest hurdles in machine learning will be creating proper training and test sets. So it's a very important concept. With that being said, I did issue the challenge in the last video to visualize these numbers on a page. We haven't done that in this video. So let's move towards that next. I'd like you to think of how could you make these more visual? Right, these are just numbers on a page right now. Maybe Matplotlib can help? Let's find out, eh? Hey, welcome back. In the last video, we split our data into training and test sets. And now, later on, we're going to be building a model to learn patterns in the training data to relate to the testing data. But as I said, right now our data is just numbers on a page. It's kind of hard to understand. You might be able to understand this, but I prefer to get visual. So let's write this down. How might we better visualize our data? And I'll put a capital here so we're grammatically correct. And this is where the Data Explorer's motto comes in. Visualize, visualize, visualize. Haha. Right, so if ever you don't understand a concept, one of the best ways to start understanding it more, for me, is to visualize it. So let's write a function to do just that. We're going to call this plot predictions. We'll see why we call it this later on. That's the benefit of making these videos, is that I've got a plan for the future. Although it might seem like I'm winging it, there is a little bit of behind the scenes happening here. So we'll have the train data, which is our X train, and then we'll have the train labels, which is our Y train, and We'll also have the test data. Yeah, that's a good idea. X test, and we'll also have the test labels equals, Y test. Excuse me, I was looking at too many X's there. And then the predictions. Now we'll set this to none because we don't have any predictions yet. But as you might have guessed, we might have some later on. So we'll put a little doc string here so that we're being nice and Pythonic. So plots training data, test data, and compares predictions. Nice and simple. Nothing too outlandish. And then we're going to create a figure. This is where matplotlib comes in. Plot figure, and we'll go fig size equals 10.7, which is my favorite hand in poker. And we'll plot the training data in blue. Also happens to be a good dimension for a matplotlib plot. Plot.scatter, train data. I'm creating a scatter plot here. We'll see what it does in a second. Color, we're going to give this a color of B for blue. That's what C stands for in matplotlib scatter. We'll go size equals 4 and label equals training data. Now, where could you find information about this scatter function here? We've got Command Shift Space. Is that going to give us a little bit of a doc string? Or sometimes if Command not space is not working, you can also hover over this bracket. I think you can even hover over this. There we go. But this is a little hard for me to read. Like it's there, but it's got a lot going on. X, Y, S, C, C map. I just like to go matplotlib scatter. There we go. We've got a whole bunch of information there. A little bit easier to read for me here. And then you can see some examples. Beautiful. So now let's jump back into here. So in our function plot predictions, we take in some training data, test data. We've got the training data plotting in blue. What color should we use for the testing data? How about green? I like that idea. Plot.scatter, test data. Green's my favorite color. What's your favorite color? C equals G. You might be able to just plot it in your favorite color here. Just remember though, it'll be a little bit different from the videos. And then we're going to call this testing data. So just the exact same line as above, but with a different set of data. Now, let's check if there are predictions. So are there predictions? So if predictions is not none, let's plot the predictions. Plot the predictions if they exist. So plot, scatter, test data. And why are we plotting the test data? Remember, what is our scatter function? Let's go back up to here. It takes in X and Y. So our predictions are going to be compared to the testing data labels. So that's the whole game that we're playing here. We're going to train our model on the training data, and then to evaluate it, we're going to get our model to predict the Y values as with the input of X test. And then to evaluate our model, we compare how good our model's predictions are, in other words, predictions, versus the actual values of the test data set. But we're going to see this in practice rather than just talk about it. So let's do our predictions in red. And label equals predictions. Wonderful. So let's also show the legend because, I mean, we're legends, so we could just put in a mirror here. No, I'm kidding. The legend is going to show our labels on the matplotlib plot. So prop equals size, and prop stands for properties. Well, it may or may not. I just like to think it does. That's how I remember it. So we have a beautiful function here to plot our data. Should we try it out? Remember, we've got hard-coded inputs here, so we don't actually need to input anything to our function. We've got our train and test data ready to go. If in doubt, run the code. Let's check it out. Did we make a mistake in our plot predictions function? You might have caught it. Hey, there we go. Beautiful. So because we don't have any predictions, we get no red dots. But this is what we're trying to do. We've got a simple straight line. You can't get a much more simple data set than that. So we've got our training data in blue and we've got our testing data in green. So the whole idea of what we're going to be doing with our machine learning model is we don't actually really need to build a machine learning model for this. We could do other things, but machine learning is fun. So we're going to take in the blue dots. So there's quite a pattern here, right? This is the relationship. We have an X value here and we have a Y value. So we're going to build a model to try and learn the pattern of these blue dots so that if we fed our model, the X values of the green dots, could it predict the appropriate Y values for that? Because remember, these are the test data set. So pass our model X test to predict Y test. So blue dots as input, green dots as the ideal output. This is the ideal output. A perfect model would have red dots over the top of the green dots. So that's what we will try to work towards. Now, we know the relationship between X and Y. How do we know that? Well, we set that up above here. This is our weight and bias. We created that line, Y equals weight times X plus bias, which is the simple version of the linear regression formula. So mx plus c, you might have heard that in high school algebra. So gradient plus intercept. That's what we've got. With that being said, let's move on to the next video and build a model. Oh, this is exciting. I'll see you there. Welcome back. In the last video, we saw how to get visual with our data. We followed the Data Explorer's motto of visualize, visualize, visualize. And we got an idea of the training data that we're working with and the testing data that we're trying to build a model to learn the patterns in the training data, essentially this upwards trend here, to be able to predict the testing data. So I just want to give you another heads up. I took a little break after recording the last video, and so now my Colab notebook has disconnected. So I'm going to click reconnect, and my variables here may not work. So this is what might happen on your end if you take a break from using Google Colab and come back. If I try to run this function, they might have been saved. Looks like they have, but if not, you can go restart and run all. This is typically one of the most helpful troubleshooting steps of using Google Colab. If a cell, say down here, isn't working, you can always rerun the cells above, and that may help with a lower cell here, such as if this function wasn't instantiated because this cell wasn't run, and we couldn't run this cell here, which calls this function here, we just have to rerun this cell above so that we can run this one. But now let's get into building our first PyTorch model. We're going to jump straight into the code. So our first PyTorch model. Now this is very exciting. Let's do it. So we'll turn this into Markdown. Now we're going to create a linear regression model. So let's look at linear regression formula again. We're going to create a model that's essentially going to run this computation. So we need to create a model that has a parameter for A, a parameter for B. In our case, it's going to be weight and bias, and a way to do this forward computation. What I mean by that, we're going to see with code. So let's do it. We'll do it with pure PyTorch. So create a linear regression model class. Now, if you're not experienced with using Python classes, I'm going to be using them throughout the course, and I'm going to call this one linear regression model. If you haven't dealt with Python classes before, that's okay. I'm going to be explaining what we're doing as we're doing it. But if you'd like a deeper dive, I'd recommend you to Real Python classes. OOP in Python 3. That's a good rhyming. So I'm just going to link this here. Because we're going to be building classes throughout the course, I'd recommend getting familiar with OOP, which is Object-Oriented Programming, a little bit of a mouthful, hence the OOP, in Python. To do so, you can use the following resource from Real Python. But we're not going to go through that now. I'd rather just code it out and talk it out while we do it. So we've got a class here. Now, the first thing you might notice is that the class inherits from nn.module. Now you might be wondering, well, what's nn.module? Well, let's write down here, almost everything in PyTorch inherits from nn.module. So you can imagine nn.module as the Lego building bricks of PyTorch model. And so nn.module has a lot of helpful inbuilt things that's going to help us build our PyTorch models. And of course, how could you learn more about it? Well, you could go nn.module PyTorch. Module. Here we go. Base class for all neural network modules. Wonderful. Your models should also subclass this class. So that's what we're building. We're building our own PyTorch model. And so the documentation here says that your models should also subclass this class. And another thing with PyTorch, this is what makes it might seem very confusing when you first begin, but modules can contain other modules. So what I mean by it being a Lego brick is that you can stack these modules on top of each other and make progressively more complex neural networks as you go. But we'll leave that for later on. For now, we're going to start with something nice and simple, and let's clean up our web browser. So we're going to create a constructor here, which is with the init function. It's going to take self as a parameter. If you're not sure of what's going on here, just follow along with the code for now, and I'd encourage you to read this documentation here after the video. So then we have super.init. I know when I first started learning this, I was like, why do we have to write init twice? And then what's super and all that jazz? But just for now, just take this as being some required Python syntax. And then we have self.weights. So that means we're going to create a weights parameter. We'll see why we do this in a second. And to create that parameter, we're going to use nn.parameter. And just a quick reminder that we imported nn from Torch before. And if you remember, nn is the building block layer for neural networks. And within nn, so nn stands for neural network, is module. So we've got nn.parameter. Now, we're going to start with random parameters. So torch.randn, 1. We're going to talk through each of these in a second. So I'm also going to put requires grad equals true. We haven't touched any of these, but that's okay. dtype equals torch.float. So let's see what nn parameter tells us. What do we have here? A kind of tensor that is to be considered a module parameter. So we've just created a module using nn module. Parameters are torch tensor subclasses. So this is a tensor in itself that have a very special property when used with modules. When they're assigned as a module attribute, they are automatically added to the list of its parameters and will appear, e.g. in module.parameters iterator. Oh, we're going to see that later on. Assigning a tensor doesn't have such effect. So we're creating a parameter here. Now, requires grad. What does that mean? Well, let's just, rather than just try to read the docstring Colab, let's look it up. nn.parameter. What does it say? Requires grad, optional, if the parameter requires gradient. What does requires gradient mean? Well, let's come back to that in a second. And then for now, I just want you to think about it. dtype equals torch.float. Now, the data type here, torch.float, is, as we've discussed before, is the default for PyTorch. Torch.float, this could also be torch.float32. So we're just going to leave it as torch float32 because PyTorch likes to work with float32. Now, do we have this by default? We do. So we don't necessarily have to set requires grad equals true. So just keep that in mind. So now we've created a parameter for the weights. We also have to create a parameter for the bias. Let's finish creating this and then we'll write the code, then we'll talk about it. So rand n now requires grad equals true and dtype equals torch.float. There we go. And now we're going to write a forward method. So forward method to define the computation in the model. So let's go def forward, which self takes in a parameter x, which is data, which x is expected to be of type torch tensor, and it returns a torch.tensor. And then we go here. And so we say x, we don't necessarily need this comment, I'm just going to write it anyway. X is the input data. So in our case, it might be the training data. And then from here, we want it to return self.weights times x plus self.bias. Now, where have we seen this before? Well, this is the linear regression formula. Now, let's take a step back into how we created our data, and then we'll go back through and talk a little bit more about what's going on here. So if we go back up to our data, where did we create that? We created it here. So you see how we've created known parameters, weight and bias. And then we created our y variable, our target, using the linear regression formula, weight times x plus bias. And x were a range of numbers. So what we've done with our linear regression model that we've created from scratch, if we go down here, we've created a parameter, weights. This could just be weight if we wanted to. We've created a parameter here. So when we created our data, we knew what the parameters weight and bias were. The whole goal of our model is to start with random numbers. So these are going to be random parameters, and to look at the data, which in our case will be the training samples, and update those random numbers to represent the pattern here. So ideally, our model, if it's learning correctly, will take our weight, which is going to be a random value, and our bias, which is going to be a random value, and it will run it through this forward calculation, which is the same formula that we use to create our data, and it will adjust the weight and bias to represent as close as possible, if not perfect, the known parameters. So that's the premise of machine learning. Now, how does it do this? Through an algorithm called gradient descent. So I'm just going to write this down because we've talked a lot about this, but I'd like to just tie it together here. So what our model does. So start with random values, weight and bias. Look at training data and adjust the random values to better represent the, or get closer to the ideal values. So the weight and bias values we use to create the data. So that's what it's going to do. It's going to start with random values and then continually look at our training data to see if it can adjust those random values to be what would represent this straight line here. Now, how does it do so? How does it do so? Through two main algorithms. So one is gradient descent, and two is back propagation. So I'm going to leave it here for the time being, but we're going to continue talking about this. Gradient descent is why we have requires grad equals true. And so what this is going to do is when we run computations using this model here, PyTorch is going to keep track of the gradients of our weights parameter and our bias parameter. And then it's going to update them through a combination of gradient descent and backpropagation. Now, I'm going to leave this as extracurricular for you to look through, gradient descent and backpropagation. I'm going to add some resources here. There will also be plenty of resources in the PyTorch Workflow Fundamentals book chapter on how these algorithms work behind the scenes. We're going to be focused on the code, the PyTorch code, to trigger these algorithms behind the scenes. So PyTorch, lucky for us, has implemented gradient descent and backpropagation for us. So we're writing the higher level code here to trigger these two algorithms. So in the next video, we're going to step through this a little bit more and then further discuss some of the most useful and required modules of PyTorch, particularly NN and a couple of others. So let's leave it there, and I'll see you in the next video. Welcome back. In the last video, we covered a whole bunch in creating our first PyTorch model that inherits from nn.module. We talked about object-oriented programming and how a lot of PyTorch uses object-oriented programming. I can't say that. I might just say OOP for now. What I've done since the last video, though, is I've added two resources here for gradient descent and backpropagation. These are two of my favorite videos on YouTube by the channel 3Blue 1Brown. So this is on gradient descent. I would highly recommend watching this entire series, by the way. So that's your extra curriculum for this video in particular and for this course overall, is to go through these two videos. Even if you're not sure entirely what's happening, you will gain an intuition for the code that we're going to be writing with PyTorch. So just keep that in mind as we go forward. A lot of what PyTorch is doing behind the scenes for us is taking care of these two algorithms for us. And we also created two parameters here in our model, where we've instantiated them as random values. So one parameter for each of the ones that we use, the weight and bias, for our data set. And now I want you to keep in mind that we're working with a simple data set here. So we've created our known parameters. But in a data set that you haven't created by yourself, you've maybe gathered that from the internet, such as images, you won't be necessarily defining these parameters. Instead, another module from NN will define the parameters for you and will work out what those parameters should end up being. But since we're working with a simple data set, we can define our two parameters that we're trying to estimate. This is a key point here, is that our model is going to start with random values. That's the annotation I've added here. Start with a random weight value using torch random. And then we've told it that it can update via gradient descent. So PyTorch is going to track the gradients of this parameter for us. And then we've told it that the D type we want is float32. We don't necessarily need these two set explicitly, because a lot of the time the default in PyTorch is to set these two, requires grad equals true and D type equals torch.float. Does that for us behind the scenes. But just to keep things as fundamental and as straightforward as possible, we've set all of this explicitly. So let's jump into the keynote. I'd just like to explain what's going on one more time in a visual sense. So here's the exact code that we've just written. I've just copied it from here and I've just made it a little bit more colorful. But here's what's going on. So when you build a model in PyTorch, it subclasses the nn.module class. This contains all the building blocks for neural networks. So our class of model subclasses nn.module. Now, inside the constructor, we initialize the model parameters. Now, as we'll see later on with bigger models, we won't necessarily always explicitly create the weights and biases. We might initialize whole layers. Now, this is a concept we haven't touched on yet, but we might initialize a list of layers or whatever we need. So basically what happens in here is that we create whatever variables that we need for our model to use. And so these could be different layers from torch.nn, single parameters, which is what we've done in our case, hard-coded values, or even functions. Now we've explicitly set requires grad equals true for our model parameters. So this in turn means that PyTorch behind the scenes will track all of the gradients for these parameters here for use with torch.autograd. So torch.autograd module of PyTorch is what implements gradient descent. Now, a lot of this will happen behind the scenes for when we write our PyTorch training code. So if you'd like to know what's happening behind the scenes, I'd highly recommend you checking out these two videos, hence is why I've linked them here. Oh, and for many pytorch.nn modules, requires grad is true is set by default. Finally, we've got a forward method. Now, any subclass of nn.module, which is what we've done, requires a forward method. Now, we can see this in the documentation. If we go torch.nn.module, click on module, do we have forward? Yeah, there we go. So forward, we've got a lot of things built into nn.module. So you see here, this is a subclass of nn.module, and then we have forward. So forward is what defines the computation performed at every call. So if we were to call linear regression model and put some data through it, the forward method is the operation that this module does, that this model does. And in our case, our forward method is the linear regression function. So keep this in mind. Any subclass of nn.module needs to override the forward method. So you need to define a forward method if you're going to subclass nn.module. We'll see this very hands-on, but for now, I believe that's enough coverage of what we've done. If you have any questions, remember, you can ask it in the discussions. We've got a fair bit going on here, but I think we've broken it down a fair bit. The next step is for us to, I know I mentioned this in a previous video, is to cover some PyTorch model building essentials, but we're going to cover a few more of them. We've seen some already, but the next way to really start to understand what's going on is to check the contents of our model, train one, and make some predictions with it. So let's get hands-on with that in the next few videos. I'll see you there. Welcome back. In the last couple of videos, we stepped through creating our first PyTorch model. And it looks like there's a fair bit going on here, but some of the main takeaways is that almost every model in PyTorch inherits from nn.module. And if you are going to inherit from nn.module, you should override the forward method to define what computation is happening in your model. And for later on, when our model is learning things, in other words, updating its weights and bias values from random values to values that better fit the data, it's going to do so via gradient descent and backpropagation. And so these two videos are some extra curriculum for what's happening behind the scenes. But we haven't actually written any code yet to trigger these two, so I'll refer back to these when we actually do write code to do that. For now, we've just got a model that defines some forward computation. But speaking of models, let's have a look at a couple of PyTorch model building essentials. So we're not going to write too much code for this video, and it's going to be relatively short, but I just want to introduce you to some of the main classes that you're going to be interacting with in PyTorch. And we've seen some of these already. So one of the first is torch.nn. So contains all of the building blocks for computational graphs. Computational graphs is another word for neural networks. Well, actually, computational graphs is quite general. I'll just write here, a neural network can be considered a computational graph. So then we have torch.nn.parameter. We've seen this. So what parameters should our model try and learn? And then we can write here, often a PyTorch layer from torch.nn will set these for us. And then we've got torch.nn.module, which is what we've seen here. And so torch.nn.module is the base class for all neural network modules. If you subclass it, you should overwrite forward, which is what we've done here. We've created our own forward method. So what else should we cover here? We're going to see these later on, but I'm going to put it here, torch.optim. This is where the optimizers in PyTorch live. They will help with gradient descent. So optimizer. An optimizer is, as we've said before, that our model starts with random values and it looks at training data and adjusts the random values to better represent the ideal values. The optimizer contains algorithm that's going to optimize these values instead of being random to being values that better represent our data. So those algorithms live in torch.optim. And then one more for now. I'll link to extra resources and we're going to cover them as we go. That's how I like to do things, cover them as we need them. So all nn.module, so this is the forward method. I'm just going to explicitly say here that all nn module subclasses require you to overwrite forward. This method defines what happens in the forward computation. So in our case, if we were to pass some data to our linear regression model, the forward method would take that data and perform this computation here. And as your models get bigger and bigger, ours is quite straightforward here. This forward computation can be as simple or as complex as you like, depending on what you'd like your model to do. And so I've got a nice and fancy slide here, which basically reiterates what we've just discussed. PyTorch essential neural network building modules. So the module torch.nn, torch.nn.module, torch.optim, torch.utils.dataset. We haven't actually talked about this yet. And I believe there's one more, data loader. We're going to see these two later on, but these are very helpful when you've got a bit more of a complicated data set. In our case, we've got just 50 integers for our data set. We've got a simple straight line, but when we need to create more complex data sets, we're going to use these. So this will help us build models. This will help us optimize our models' parameters, and this will help us load data. And if you'd like more, one of my favorite resources is the PyTorch cheat sheet. Again, we're referring back to the documentation. See, all of this documentation, right? As I said, this course is not a replacement for the documentation. It's just my interpretation of how one should best become familiar with PyTorch. So we've got imports, the general, import torch, from torch.utils.data, we've got dataset, data loader. Oh, would you look at that? We've got that mentioned here, dataset, data loader. And torch script and JIT, neural network API, ONNX. I'll let you go through here. We're covering some of the most fundamental ones here, but there's, of course, PyTorch is quite a big library. So some extracurricular for this video would be to go through this for 5 to 10 minutes and just read. You don't have to understand them all. We're going to start to get more familiar with all of these. Well, not all of them, because I mean, that would require making videos for the whole documentation, but a lot of these through writing them via code. So that's enough for this video. I'll link this PyTorch cheat sheet in the video here. And in the next video, how about we haven't actually checked out what happens if we do create an instance of our linear regression model. I think we should do that. I'll see you there. Welcome back. In the last video, we covered some of the PyTorch model building essentials. And look, I linked a cheat sheet here. There's a lot going on. There's a lot of text going on the page. Of course, the reference material for here is in the Learn PyTorch book. PyTorch Model Building Essentials under 0.1, which is the notebook we're working on here, but I couldn't help myself. I wanted to add some color to this. So before we inspect our model, let's just add a little bit of color to our text on the page. We go to, here's our workflow. This is what we're covering in this video, right? Or in this module, 0.1. But to get data ready, here are some of the most important PyTorch modules. Torch vision.transforms, we'll see that when we cover computer vision later on. Torch.utils.data.dataset, so that's if we want to create a dataset that's a little bit more complicated, then because our dataset is so simple, we haven't used either of these dataset creator or data loader. Then if we go build or pick a model, well, we can use torch.nn. We've seen that one. We've seen torch.nn.module. So in our case, we're building a model. But if we wanted a pre-trained model, well, there's some computer vision models that have already been built for us in torchvision.models. Now, Torch Vision stands for PyTorch's computer vision module. So we haven't covered that either, but this is just a spoiler for what's coming on later on. Then at the optimizer, if we wanted to optimize our model's parameters to better represent a data set, we can go to torch.optim. Then if we wanted to evaluate the model, Well, we've got torch metrics for that. We haven't seen that, but we're going to be hands-on with all of these later on. Then if we wanted to improve through experimentation, we've got torch.utils.tensorboard. What's this? But again, if you want more, there's some at the PyTorch cheat sheet. But now this is just adding a little bit of color and a little bit of code to our PyTorch workflow. And with that being said, let's get a little bit deeper into what we've built, which is our first PyTorch model. So checking the contents of our PyTorch model. So now we've created a model. Let's see what's inside. You might already be able to guess this by the fact of what we've created in the constructor here, in the init function. So what do you think we have inside our model? And how do you think we'd look in that? Now, of course, these are questions you might not have the answer to because you're like, Daniel, I'm just starting to learn PyTorch. I don't know these, but I'm asking you just to start thinking about these different things, you know? So we can check out our model parameters or what's inside our model using, wait for it, dot parameters. Oh, don't you love it when things are nice and simple? Well, let's check it out, hey? Well, first things we're going to do is let's create a random seed. Now, why are we creating a random seed? Well, because recall, we're creating these parameters with random values. And if we were to create them without a random seed, we would get different values every time. So for the sake of the educational sense, for the sake of this video, we're going to create a manual seed here, torch.manualSeed. I'm going to use 42, or maybe 43. I could use 43 now. 42, because I love 42. It's the answer to the universe. And we're going to create an instance of the model that we created. So this is a subclass of nn.module. So let's do it. Model 0, because it's going to be the 0th model, the first model that we've ever created in this whole course. How amazing. Linear regression model, which is what our class is called. So we can just call it like that. That's all I'm doing, just calling this class. And so let's just see what happens there. And then if we go model 0, what does it give us? Oh, linear regression model. Okay, it doesn't give us much. But we want to find out what's going on in here. So check out the parameters. So model 0 dot parameters. What do we get from this? Oh, a generator. Well, let's turn this into a list. That'll be better to look at. There we go. Oh, how exciting is that? So parameter containing. Oh, look at the values. Tensor requires grad equals true. Parameter containing. Wonderful. So these are our model parameters. So why are they the values that they are? Well, it's because we've used torch rand n. Let's see what happens if we go, let's just create torch.randn1. What happens? We get a value like that. And now if we run this again, we get the same values. But if we run this again, so keep this in mind, 2, 3, 4, 5, actually that's pretty cool that we got a random value that was all in order, 4 in a row. Can we do it twice in a row? Probably not. Oh, we get it the same one. Now why is that? Oh, we get a different one. Did we just get the same one twice? Oh my gosh, we got the same value twice in a row. You saw that. You saw that. That's incredible. Now the reason why we get this is because this one is different every time because there's no random seed. Watch if we put the random seed here. Torch.manualSeed 42 3367. What happens? 3367. What happens? 3367. Okay? And what if we commented out the random seed here? Initialized our model. Different values. 235. 2345. It must like that value. Oh my goodness. Let me know if you get that value. Right? So if we keep going, we get different values every single time. Why is this? Why are we getting different values every single time? You might be, Daniel, you sound like a broken record, but I'm trying to really drive home the fact that we initialize our models with random parameters. So this is the essence of what our machine learning models and deep learning models are going to do. Start with random values, weights and bias. We've only got 2 parameters here, but the future models that we build might have thousands. And so, of course, we're not going to do them all by hand. We'll see how we do that later on. But for now, we start with random values, and our ideal model will look at the training data and adjust these random values. But just so that we can get reproducible results, I'll get rid of this cell. I've set the random seed here. So you should be getting similar values to this. If you're not, because there's maybe some sort of PyTouch update in how the random seed's calculated, you might get slightly different values. But for now, we'll use torch.manual sieve.42. And I want you to just be aware of, this can be a little bit confusing if you just do the list of parameters. For me, I understand it better if I list the name parameters. So the way we do that is with model 0, and we call stateDict on it. This is going to give us our dictionary of the parameters of our model. So as you can see here, we've got weights and we've got bias, and they are random values. So where did weights and bias come from? Well, of course, they came from here, weights, bias, but of course, as well up here, we've got known parameters. So now our whole goal is what? Our whole goal is to build code or write code that is going to allow our model to look at these blue dots here and adjust this weight and bias value to be weights as close as possible to weight and bias. Now, how do we go from here and here to here and here? Well, we're going to see that in future videos, but the closer we get these values to these two, the better we're going to be able to predict and model our data. Now, this principle, I cannot stress enough, is the fundamental foundation, wow, good description, Daniel. The entire foundation of deep learning. We start with some random values, and we use gradient descent and backpropagation plus whatever data that we're working with to move these random values as close as possible to the ideal values. And in most cases, you won't know what the ideal values are. But in our simple case, we already know what the ideal values are. So just keep that in mind going forward. The premise of deep learning is to start with random values and make them more representative, closer to the ideal values. With that being said, let's try and make some predictions with our model as it is. I mean, it's got random values. How do you think the predictions will go? So I think in the next video, we'll make some predictions on this test data and see what they look like. I'll see you there. Welcome back. In the last video, we checked out the internals of our first PyTorch model. And we found out that because we're creating our model with or the parameters of our model, with torch.rand, they begin as random variables. And we also discussed the entire premise of deep learning is to start with random numbers and slowly progress those towards more ideal numbers, slightly less random numbers based on the data. So let's see, before we start to improve these numbers, let's see what their predictive power is like right now. Now you might be able to guess how well these random numbers will be able to predict on our data. If you're not sure what that predicting means, let's have a look. So making predictions using torch.inference mode. Something we haven't seen, but as always, we're going to discuss it while we use it. So to check our model's predictive power, let's see how well it predicts y-test based on x-test. Because remember, again, another premise of a machine learning model is to take some features as input and make some predictions close to some sort of labels. So when we pass data through our model, it's going to run it through the forward method. So here's where it's a little bit confusing. We defined a forward method and it takes x as input. Now I've done a little x, but we're going to pass it in a large X as its input. But the reason why I've done a little x is because oftentimes in PyTorch code you're going to find all over the internet is that x is quite commonly used in the forward method here, like this, as the input data. So I've just left it there because that's what you're going to find quite often. So let's test it out. We haven't discussed what inference mode does yet, but we will. Make predictions with model. So with torch.inference mode, let's use it, and then we will discuss what's going on. ypreds equals model 0 x test. So that's all we're doing. We're passing the x test data through our model. Now, when we pass this x test in here, let's remind ourselves of what x test is. X test. 10 variables here, and we're trying to, our ideal model will predict the exact values of y test. So this is what our model will do if it's a perfect model. It will take these x test values as input, and it will return these y test values as output. That's an ideal model. So the predictions are the exact same as the test data set. How do you think our model will go, considering it's starting with random values as its parameters? Well, let's find out, hey? So we'll can that. ypreds. Oh, what's happened here? Not implemented error. This is an error I get quite often in Google Colab when I'm creating a PyTorch model. Now, it usually happens. I'm glad we've stumbled upon this, and I think I know the fix, but if not, we might see a little bit of troubleshooting in this video, is that when we create this, if you see this not implemented error, right, it's saying that the forward method, here we go, forward unimplemented, there we go. It's a little bit of a rabbit hole, this not implemented error. I've come across it a fair few times, and it took me a while to figure out that for some reason the spacing, so in Python, you know how you have space, space, and that defines a function, space, space, there's another thing there, and another line there. For some reason, if you look at this line in my notebook, and by the way, if you don't have these lines, or if you don't have these numbers, you can go into Tools, Settings, Editor, and then you can define them here. So show line numbers, show indentation guides, all that sort of jazz there. You can customize what's going on, but I just have these two on because I've run into this error a fair few times. And so it's because that this forward method is not in line with this bracket here. So we need to highlight this and click Shift Tab, move it over. So now you see that it's in line here. And then if we run this, it won't change any output there. See, that's the hidden gotcha, is that when we ran this before, it found no error. But then when we run it down here, it works. So just keep that in mind. I'm really glad we stumbled upon that because indentation errors, not implemented errors, one of the most common errors you'll find in PyTorch or in, well, when you're writing PyTorch code in Google Colab. I'm not sure why, but it just happens. So these are our model's predictions so far by running the test data through our model's forward method that we defined. And so if we look at y test, are these close? Oh my gosh, they are shocking. So why don't we visualize them? Plot predictions. And we're going to put in predictions equals ypreds. Let's have a look. Oh my goodness. All the way over here. Remember how we discussed before that an ideal model will have, what? Red dots on top of the green dots because our ideal model will be perfectly predicting the test data. So right now, because our model is initialized with random parameters, it's basically making random predictions. So they're extremely far from where our ideal predictions are, is that we'll have some training data and our model predictions when we first create our model will be quite bad. But we want to write some code that will hopefully move these red dots closer to these green dots. We're going to see how we can do that in later videos. But we did one thing up here which we haven't discussed, which is with torch.inference mode. Now, this is a context manager, which is what happens when we're making predictions. So making predictions, another word for predictions is inference. Torch uses inference, so I'll try to use that a bit more, but I like to use predictions as well. We could also just go ypreds equals model 0 dot x test. And we're going to get quite a similar output. Right? But I've put on inference mode because I want to start making that a habit for later on when we make predictions. Put on inference mode. Now, why do this? You might notice something different. What's the difference here between the outputs? ypreds equals model. There's no inference mode here, no context manager. Do you notice that there's a grad function here? Now, we don't need to go into discussing what exactly this is doing here. But do you notice that this one is lacking that grad function? So do you remember how behind the scenes I said that PyTorch does a few things with requires grad equals true? It keeps track of the gradients of different parameters so that they can be used in gradient descent and backpropagation. Now, what inference mode does is it turns off that gradient tracking. So it essentially removes all of the, because when we're doing inference, we're not doing training, so we don't need to keep track of the gradient. So we don't need to keep track of how we should update our models. So inference mode disables all of the useful things that are available during training. What's the benefit of this? Well, it means that PyTorch behind the scenes is keeping track of less data. So in turn, it will, with our small data set, it probably won't be too dramatic. But with a larger data set, it means that your predictions will potentially be a lot faster because a whole bunch of numbers aren't being kept track of, or a whole bunch of things that you don't need during prediction mode or inference mode, that's why it's called inference mode, are not being saved to memory. If you'd like to learn more about this, you go PyTorch inference mode Twitter. I just remember to search for Twitter because they did a big tweet storm about it. Here we go. So, this is another thing that we can cover. I'm going to copy this in here, but there's also a blog post about what's going on behind the scenes. Long story short, it makes your code faster. Want to make your inference code in PyTorch run faster? Here's a quick thread on doing exactly that. And that's what we're doing. So I'm going to write down here, see more on inference mode here. And I just want to highlight something as well, is that they referenced Torch NoGrad with the Torch Inference Mode Context Manager. Inference mode is fairly new in PyTorch, so you might see a lot of code, existing PyTorch code with torch.nograd. You can use this as well, ypreds equals model 0, and this will do much of the same as what inference mode is doing, but inference mode has a few things that are advantageous over nograd, which are discussed in this thread here. But if we do this, we get very similar output to what we got before. Grad function. But as you'll read in here and in the PyTorch documentation, inference mode is the favored way of doing inference for now. I just wanted to highlight this. So you can also do something similar with torch.nograd. However, inference mode is preferred. Alrighty, so I'm just going to comment this out. So we just have one thing going on there. The main takeaway from this video is that when we're making predictions, we use the context manager torch.inference mode. And right now, because our model's variables or internal parameters are randomly initialized, our model's predictions are as good as random. So they're actually not too far off where like our values are. At least the red dots aren't like scattered all over here. But in the upcoming videos, we're going to be writing some PyTorch training code to move these values closer to the green dots by looking at the training data here. So with that being said, I'll see you in the next video. Friends, welcome back. In the last video, we saw that our model performs pretty poorly. Like, ideally, these red dots should be in line with these green dots. And we know that because why? Well, it's because our model is initialized with random parameters. And I just want to put a little note here. You don't necessarily have to initialize your model with random parameters. You could initialize it with, this could be 0 here, these two values, weights and bias could be 0, and you could go from there. Or you could also use the parameters from another model. But we're going to see that later on. That's something called transfer learning. That's just a little spoiler for what's to come. And so we've also discussed that an ideal model will replicate these known parameters. So in other words, start with random unknown parameters, these two values here, and then we want to write some code for our model to move towards estimating the ideal parameters here. Now, I just want to be explicit here and write down some intuition before we jump into the training code, but this is very exciting. We're about to get into training our very first machine learning model. So let's write here, the whole idea of training is for a model to move from some unknown parameters, these may be random, to some known parameters. Or in other words, from a poor representation of the data to a better representation of the data. And so in our case, would you say that our model's representation of the green dots here with this red dots, is that a good representation or is that a poor representation? I mean, I don't know about you, but I would say that to me, this is a fairly poor representation. And one way to measure the representation between your model's outputs, in our case, the red dots, the predictions, and the testing data, is to use a loss function. So I'm going to write this down here. This is what we're moving towards. We're moving towards training, but we need a way to measure how poorly our model's predictions are doing. So one way to measure how poor or how wrong your model's predictions are is to use a loss function. And so if we go PyTorch loss functions, we're going to see that PyTorch has a fair few loss functions built in, but the essence of all of them is quite similar. So just wait for this to load. My internet's going a little bit slow today, but that's okay. We're not in a rush here. We're learning something fun. If I search here for loss functions, here we go. So yeah, this is torch_nn. These are the basic building blocks for graphs. Whole bunch of good stuff in here, including loss functions. Beautiful. And this is another thing to note as well, another one of those scenarios where there's more words for the same thing. You might also see a loss function referred to as a criterion. There's another word called cost function. So I might just write this down so you're aware of it. Yeah, cost function versus loss function. There may be some formal definitions about what all of these are. Maybe they're used in different fields. But in the case of, we're focused on machine learning, right? So I'm just going to go note, loss function may also be called cost function or criterion in different areas. For our case, we're going to refer to it as a loss function. And let's just formally define a loss function here because we're going to go through a fair few steps in the upcoming videos. So this is a warning, nothing we can't handle, but I want to put some formal definitions on things. We're going to see them in practice. That's what I prefer to do rather than just sit here defining stuff. This lecture's already had enough text on the page. So hurry up and get into coding, Daniel. A loss function is a function to measure how wrong your model's predictions are to the ideal outputs. So lower is better. So ideally, think of a measurement. How could we measure the difference between the red dots and the green dots? One of the simplest ways to do so would be just measure the distance here, right? So if we go, let's just estimate this as 0.35 to 0.8 thereabouts. So what's the difference there? About 0.45. Then we could do the same again for all of these other dots and then maybe take the average of that. Now, if you've worked with loss functions before, you might have realized that I've just reproduced mean absolute error. But we're going to get to that in a minute. So we need a loss function. I'm going to write down another little dot point here. This is just setting up intuition. Things we need to train. We need a loss function. This is PyTorch, and this is machine learning in general, actually. But we're focused on PyTorch. We need an optimizer. what does the optimizer do? Takes into account the loss of a model and adjusts the model's parameters. So the parameters, recall, are our weight and bias values, weight and biases. We can check those, or bias. We can check those by going model.parameter or parameters. But I also like, oh, that's going to give us a generator, isn't it? Oh, did we not define the model yet? What do we call our model? Oh, model 0. Excuse me. I forgot. We're going to build a lot of models in this course, so we're giving them numbers. Model.parameters, yeah, we've got a generator. So we'll turn that into a list. But model 0, if we want to get them labeled, we want state dict here. There we go. So our weights is this value. That's a random value we've set, and there's the bias. And now we've only got 2 parameters for our model, so it's quite simple. However, the principles that we're learning here are going to be the same principles, taking a loss function, trying to minimize it, so getting it to lower, so the ideal model will predict exactly what our test data is. And an optimizer will take into account the loss and will adjust a model's parameter, in our case, weights and bias, to be, let's finish this definition, takes into account the loss of a model and adjusts the model's parameters, e.g. weight and bias, in our case, to improve the loss function. And specifically for PyTorch, we need a training loop and a testing loop. Now, this is what we're going to work towards building throughout the next couple of videos. Probably going to focus on these 2 first, the loss function and optimizer. There's the formal definition of those. You're going to find many different definitions. That's how I'm going to define them. Loss function measures how wrong your model's predictions are. Lower is better. Optimizer takes into account the loss of your model, so how wrong it is, and starts to move these 2 values into a way that improves where these red dots end up. But these, again, these principles of a loss function and an optimizer can be for models with 2 parameters or models with millions of parameters. Can be for computer vision models, or could be for simple models like ours that predict the dots on a straight line. So with that being said, let's jump into the next video. We'll start to look a little deeper into loss function for our problem and an optimizer. I'll see you there. Welcome back. Whew, we're in an exciting streak of videos coming up here. I mean, the whole course is fun, trust me, but this is really exciting because training your first machine learning model seems a little bit like magic, but it's even more fun when you're writing the code yourself, what's going on behind the scenes. So we discussed that the whole concept of training is from going unknown parameters, random parameters, such as what we've got so far, to parameters that better represent the data. And we spoke of the concept of a loss function. We want to minimize the loss function. That is the whole idea of a training loop in PyTorch, or an optimization loop in PyTorch. And an optimizer is one of those ways that can nudge the parameters of our model, in our case, weights or bias, towards values, rather than just being random values like they are now, towards values that lower the loss function. And if we lower the loss function, what does the loss function do? It measures how wrong our model's predictions are compared to the ideal outputs. So if we lower that, well, hopefully we move these red dots towards the green dots. And so, as you might have guessed, PyTorch has some built-in functionality for implementing loss functions and optimizers. And by the way, what we're covering so far is in the train model section of the PyTorch workflow fundamentals. I've got a little nice table here which describes a loss function. What does it do? Where does it live in PyTorch? Common values. We're going to see some of these hands-on. If you'd like to read about it, of course, you have the book version of the course here. So, loss functions in PyTorch. I'm just in docs, torch.nn. Look at this. Look at all these loss functions. There's far too many for us to go through all in one hit. So we're just going to focus on some of the most common ones. Look at that. We got about, what's that, 15 loss functions, something like that? Well, truth be told is that which one should you use? You're not really going to know unless you start to work hands-on with different problems. And so in our case, we're going to be looking at L1 loss. And this is, again, once more, another instance where Different machine learning libraries have different names for the same thing. This is mean absolute error, which we kind of discussed in the last video, which is if we took the distance from this red dot to this green dot and say it's 0.4, thereabouts, 0.4, 0.4, and then took the mean, well, we've got the mean absolute error. But in PyTorch, they call it L1 loss, which is a little bit confusing because then we go to MSE loss, which is mean squared error, which is L2. So naming conventions just takes a little bit of getting used to. This is a warning for you. So let's have a look at the L1 loss function. Again, I'm just making you aware of where the other loss functions are. We'll do with some binary cross entropy loss later in the course. And maybe even, is there categorical cross entropy? We'll see that later on. But all the others will be problem specific. For now, a couple of loss functions like this, L1 loss, MSE loss, we use for regression problems. So that's predicting a number. Cross entropy loss is a loss that you use with classification problems. But we'll see those hands-on later on. Let's have a look at L1 loss. So L1 loss creates a criterion. As I said, you might hear the word criterion used in PyTorch for a loss function. I typically call them loss functions. The literature typically calls it loss functions. That measures the mean absolute error. There we go. L1 loss is the mean absolute error between each element in the input X and target Y. Now, your extracurriculum, as you might have guessed, is to read through the documentation for the different loss functions, especially L1 loss. But for the sake of this video, let's just implement it for ourselves. Oh, and if you want a little bit of a graphic, I've got one here. This is where we're up to, by the way, picking a loss function optimizer for step 2. This is a fun part, right? We're getting into training a model. So we've got mean absolute error. Here's that graph we've seen before. Oh, look at this. Okay, so we've got the difference here. I've actually measured this before in the past, so I kind of knew what it was. Mean absolute error is if we repeat for all samples in our set that we're working with, and if we take the absolute difference between these two dots, well, then we take the mean. We've got mean absolute error. So MAE loss equals torch mean. We could write it out. That's the beauty of PyTorch, right? We could write this out. Or we could use the torch NN version, which is recommended. So let's jump in. There's a colorful slide describing what we're about to do. So let's go set up a loss function. And then we're also going to put in here, set up an optimizer. So let's call it loss fn equals nn.l1 loss. Simple as that. And then if we have a look at what's our loss function, what does this say? My goodness, my internet is going quite slow today. It's raining outside, so there might be some delays somewhere. But that's all right. It gives us a chance to sit here and be mindful about what we're doing. Look at that. Okay, loss function, L1 loss, beautiful. So we've got a loss function. Our objective for training a machine learning model will be to, let's go back, look at the colorful graphic, will be to minimize these distances here, and in turn, minimize the overall value of MAE. That is our goal. If our red dots line up with our green dots, we will have a loss value of 0, the ideal point for a model to be. And so let's go here. We now need an optimizer. As we discussed before, the optimizer takes into account the loss of a model. So these two work in tandem. That's why I've put them as similar steps if we go back a few slides. So this is why I put these as 2.1. Often picking a loss function and optimizer in PyTorch come as part of the same package because they work together. The optimizer's objective is to give the model values, so parameters like a weight and a bias, that minimize the loss function. They work in tandem. And so let's see what an optimizer. Optimizers, where might that be? What if we search here? I typically don't use this search because I prefer just using Google search, but does this give us optimizer? Hey, there we go. So again, PyTorch has torch.optim, which is where the optimizers are. Torch.optim, let me put this link in here. This is another bit of your extra curriculum if you want to read more about different optimizers in PyTorch. As you might have guessed, they have a few. TorchOptim is a package implementing various optimization algorithms. Most commonly used methods are already supported, and the interface is general enough so that more sophisticated ones can also be easily integrated into the future. So if we have a look at what algorithms exist here, again, we're going to throw a lot of names at you, but in the literature, a lot of them that have made it into here are already good working algorithms. So it's a matter of picking whichever one's best for your problem. How do you find that out? Well, SGD, stochastic gradient descent, is possibly the most popular. However, there are some iterations on SGD, such as Atom, which is another one that's really popular. So again, this is one of those other machine learning is part art, part science, is trial and error of figuring out what works best for your problem. For us, we're going to start with SGD because it's the most popular. And if you were paying attention to a previous video, you might have seen that I said, look up gradient descent. Where have we got this? Gradient descent. There we go. So this is one of the main algorithms that improves our models. So gradient descent and backpropagation. So if we have a look at this, stochastic gradient descent, bit of a tongue twister, is random gradient descent. So that's what stochastic means. So basically our model improves by taking random numbers, let's go down here, and randomly adjusting them so that they minimize the loss. And once our optimizer, that's right here, once our optimizer, torch.optim, let's implement SGD, stochastic gradient descent. We're going to write this here, stochastic gradient descent. It starts by randomly adjusting these values. And once it's found some random values or random steps that have minimized the loss value, we're going to see this in action later on, it's going to continue adjusting them in that direction. So say it says, oh, weights, if I increase the weights, it reduces the loss. So it's going to keep increasing the weights until the weights no longer reduce the loss. Maybe it gets to a point at, say, 0.65. If you increase the weights anymore, the loss is going to go up. So the optimizer is like, well, I'm going to stop there. And then for the bias, the same thing happens. If it decreases the bias and finds that the loss increases, well, it's going to go, well, I'm going to try increasing the bias instead. So again, one last summary of what's going on here. A loss function measures how wrong our model is, and the optimizer adjusts our model parameters, no matter whether there's 2 parameters or millions of them, to reduce the loss. There are a couple of things that an optimizer needs to take in. It needs to take in as an argument, params. So this is, if we go to SGD, I'm just going to link this as well. SGD, there's the formula of what SGD does. I look at this and I go, there's a lot going on here. It took me a while to understand that, so I like to see it in code. So we need params. This is short for what parameters should I optimize as an optimizer. And then we also need an LR, which stands for, I'm going to write this in a comment, LR equals learning rate. Possibly the most, oh, I didn't even type rate, did I? Possibly the most important hyperparameter you can set. So let me just remind you, I'm throwing lots of words out here, but I'm kind of like trying to write notes about what we're doing. Again, we're going to see these in action in a second. So check out our models and parameters. So a parameter is a value that the model sets itself. So learning rate equals possibly the most important learning hyperparameter. Oh no, I don't need learning there, do I? Hyperparameter. And a hyperparameter is a value that us as a data scientist or a machine learning engineer set ourselves. You can set. So the learning rate is, in our case, let's go 0.01. You're like, Daniel, where did I get this value from? Well, again, these type of values come with experience. I think it actually says it in here. LR 0.1. Yeah, okay, so the default is 0.1. But then if we go back to optim, I think I saw it somewhere. Did I see it somewhere? 0 point something, 0? Yeah, there we go. Yeah, so a lot of the default settings are pretty good in Torch optimizers. However, the learning rate, what does it actually do? We could go 0.01. These are all common values here. 0001. I'm not sure exactly why. Oh, model, it's model 0. The learning rate says to our optimizer, yes, it's going to optimize our parameters here, but the higher the learning rate, the more it adjusts each of these parameters in one hit. So let's say it's 0.01 and it's going to optimize this value here. So it's going to take that big of a step. If we changed it to here, it's going to take a big step on this 3. And if we changed it to all the way to the end, 0.01, it's only going to change this value. So the smaller the learning rate, the smaller the change in the parameter. The larger the learning rate, the larger the change in the parameter. So we've set up a loss function, we've set up an optimizer. Let's now move on to the next step in our training workflow, and that's by building a training loop. Far out. This is exciting. I'll see you in the next video. Welcome back. In the last video, we set up a loss function and we set up an optimizer and we discussed the roles of each. So the loss function measures how wrong our model is. The optimizer talks to the loss function and goes, well, if I change these parameters a certain way, does that reduce the loss function at all? And if it does, yes, let's keep adjusting them in that direction. If it doesn't, let's adjust them in the opposite direction. And I just want to show you, I added a little bit of text here just to concretely put down what we were discussing. Inside the optimizer, you'll often have to set 2 parameters, params and LR, where params is the model parameters you'd like to optimize. For an example, in our case, params equals our model 0 parameters, which were, of course, a weight and a bias, and the learning rate, which is LR in optimizer. LR stands for learning rate. And the learning rate is a hyperparameter. Remember, a hyperparameter is a value that we, the data scientist or machine learning engineer, sets, whereas a parameter is what the model sets itself. Defines how big or small the optimizer changes the model parameters. So a small learning rate, so the smaller this value, results in small changes. A large learning rate results in large changes. So another question might be, well, very valid question. Hey, I put this here already. Is which loss function and which optimizer should I use? So this is another tough one because it's problem specific. But with experience in machine learning, I'm showing you one example here. You'll get an idea of what works for your particular problem. For a regression problem like ours, a loss function of L1 loss, which is MAE in PyTorch, and an optimizer like torch.optim/SGD, like stochastic gradient descent, will suffice. But for a classification problem, we're going to see this later on. Not this one specifically, whether a photo is a cat or a dog. That's just an example of a binary classification problem. You might want to use a binary classification loss. But with that being said, we now are moving on to, well, here's our whole goal, is to reduce the MAE of our model. Let's get the workflow. We've done these 2 steps. Now we want to build a training loop. So let's get back into here. There's going to be a fair few steps going on. We've already covered a few, but hey, nothing we can't handle together. So building a training loop in PyTorch. So I thought about just talking about what's going on in a training loop, but we can talk about the steps after we've coded them. How about we do that? So we want to build a training loop and a testing loop. How about we do that? So a couple of things we need in a training loop. So there's going to be a fair few steps here if you've never written a training loop before, but that is completely fine because you'll find that the first couple of times that you write this, you'll be like, oh my gosh, there's too much going on here. But then when you have practice, you'll go, okay, I see what's going on here. And then eventually you'll write them with your eyes closed. I've got a fun song for you to help you out remembering things. It's called the Unofficial PyTorch Optimization Loop Song. We'll see that later on, or actually I'll probably leave that as an extension. But you'll see that you can also functionize these things, which we will do later in the course so that you can just write them once and then forget about them. But we're going to write it all from scratch to begin with so we know what's happening. So we want to, or actually step 0 is loop through the data. So we want to look at the data multiple times because our model is going to, at first, start with random predictions on the data, make some predictions. We're trying to improve those. We're trying to minimize the loss. To make those predictions, we do a forward pass. So forward pass, why is it called a forward pass? So this involves data moving through our model's forward functions. Now, I say functions because there might be plural, there might be more than one. And the forward method, recall, we wrote in our model up here. Forward. A forward pass is our data going through this function here. And if you want to look at it visually, let's look up a neural network graphic. Images, a forward pass is just data moving from the input to the output layer. So starting here, input layer, moving through the model. So that's a forward pass. Also called forward propagation. Another time where more than one name is used for the same thing. So we'll go back down here, forward pass, and I'll just write here, also called forward propagation. Propagation. Wonderful. And then we need to calculate the loss. So forward pass, let me write this. To calculate or to make predictions on data. So calculate the loss, compare forward pass predictions. Oh, there's some thunder going in the background here of my place. We might be in for a storm. Perfect time to write code. Compare forward pass predictions to ground truth labels. We're going to see all this in code in a second. Calculate the loss, and then we're going to go optimize a zero grad. We haven't spoken about what this is, but that's okay. We're going to see that in a second. I'm not going to put too much there. Loss backward. We haven't discussed this one either. There's probably 3 steps that we haven't really discussed. We've discussed the idea behind them, but not too much in depth. Optimizer step. So this one is loss backwards is move backwards. If the forward pass is forwards, like through the network, the forward pass is data goes in to out. The backward pass data goes, or calculations happen backwards. So we'll see what that is in a second. Where were we? Over here. We've got too much going on. I'm getting rid of these. Moves backwards through the network to calculate the gradients. The gradients of each of the parameters of our model with respect to the loss. Oh my gosh, that is an absolute mouthful, but that'll do for now. Optimizer step. This is going to use the optimizer to adjust our model's parameters to try and improve the loss. So, remember how I said in a previous video that I'd love you to watch the 2 videos I linked above, one on gradient descent and one on backpropagation. If you did, you might have seen like there's a fair bit of math going on in there. Well, that's essentially how our model goes from random parameters to better parameters using math. Many people, one of the main things I get asked from machine learning is how do I learn machine learning if I didn't do math? Well, the beautiful thing about PyTorch is that it implements a lot of the math of backpropagation. So this is backpropagation. I'm going to write this down here. This is an algorithm called backpropagation, hence the loss backward. We're going to see this in code in a second, don't you worry. And this is gradient descent. So these 2 algorithms drive the majority of our learning. So backpropagation, calculate the gradients of the parameters of our model with respect to the loss function, and optimizer step will trigger code to run gradient descent, which is to minimize the gradients. Because what is a gradient? Let's look this up. What is a gradient? I know we haven't written the code yet, but we're going to do that. Images. Gradient, there we go. Change in y, change in x. Gradient is from high school math. A gradient is a slope. So if you were on a hill, let's find a picture of a hill. Picture of a hill. There we go. This is a great big hill. So, if you were on the top of this hill and you wanted to get to the bottom, how would you get to the bottom? Well, of course, you just walk down the hill. But if you're a machine learning model, what are you trying to do? Let's imagine your loss is the height of this hill. And you start off with your loss is really high. And you want to take your loss down to 0, which is the bottom, right? Well, if you measure the gradient of the hill, the bottom of the hill is in the opposite direction to where the gradient is steep. Does that make sense? So if the gradient here is an incline, we want our model to move towards the gradient being nothing, which is down here. And you could argue, yeah, the gradient's probably nothing up the top here, but let's just, for argument's sake, say that we want to get to the bottom of the hill. So we're measuring the gradient, and one of the ways an optimization algorithm works is it moves our model parameters so that the gradient equals 0. And then if the gradient of the loss equals 0, well, the loss equals 0 too. So now let's write some code. So we're going to set up a parameter called, or a variable called epochs, and we're going to start with 1. Even though this could be any value, let me define these as we go. So we're going to write code to do all of this. So epochs. An epoch is one loop through the data. ... So epochs, we're going to start with 1. So one time through all of the data. We don't have much data. And so for epoch, so let's go this. This is step 0. 0, loop through the data. By the way, when I say loop through the data, I want you to do all of these steps within the loop. And do ... loop through the data. So for epoch in range epochs. Even though it's only going to be 1, we can adjust this later. And because epochs, we've set this ourselves, this is a hyperparameter because we've set it ourselves. And I know you could argue that, hey, our machine learning parameters of model 0, or our model parameters, model 0, aren't actually parameters because we've set them. But in the models that you build in the future, they will likely be set automatically rather than you setting them explicitly like we've done when we created model 0. And oh my gosh, this is taking quite a while to run. That's all right. We don't need it to run fast. We need to write some more code, Daniel. Come on. There's a step here I haven't discussed either. Set the model to training mode. So PyTorch models have a couple of different modes. The default is training mode. So we can set it to training mode by going like this. Train. So what does train mode do in a PyTorch model? My goodness, is there a reason my internet is going this slow? Well, that's all right. I'm just going to discuss this with talking. Again, list. Train mode. Train mode in PyTorch sets, oh, there we go, requires grad equals true. Now I wonder if we do with torch.nograd, remember nograd is similar to inference mode, will this adjust? See, I just wanted you to take note of requires grad equals true. Actually, what I might do is we do this in a different cell. Watch this. This is just going to be, rather than me just spit words at you, I reckon we might be able to get it working doing this. Oh, that didn't list the model parameters. Why did that not come out? Model 0.eval. So there's two modes, eval mode and train mode. Model.eval parameters. Okay, we're experimenting together on the fly here, and actually this is what I want you to do, is I want you to experiment with different things. It's not going to say requires grad equals false. With torch.nograd. Model 0.parameters. I don't know if this will work, but it definitely works behind the scenes. And what I mean by works behind the scenes and not here, it works behind the scenes when calculations are being made, but not if we're trying to explicitly print things out. Well, that's an experiment that I thought was going to work and it didn't work. So train mode in PyTorch sets all parameters that require gradients to require gradients. So do you remember with the picture of the hill, I spoke about how we're trying to minimize the gradient? So the gradient is the steepness of the hill. If the height of the hill is a loss function and we want to take that down to 0, we want to take the gradient down to 0. So same thing with the gradients of our model parameters, which are here, with respect to the loss function, we want to try and minimize that gradient. So that's gradient descent, is take that gradient down to 0. So model.train, and then there's also model 0.eval, so turns off gradient tracking. So we're going to see that later on. But for now, I feel like this video is getting far too long. Let's finish the training loop in the next video. I'll see you there. Friends, welcome back. In the last video, I promised a lot of code, but we didn't get there. We discussed some important steps. I forgot how much behind the scenes there is to a PyTorch training loop. And I think it's important to spend the time that we did discussing what's going on, because there's a fair few steps, but once you know what's going on, I mean, later on, we don't have to write all the code that we're going to write in this video. You can functionize it. We're going to see that later on in the course, and it's going to run behind the scenes for us. But we're spending a fair bit of time here because this is literally the crux of how our model learns. So let's get into it. So now we're going to implement the forward pass, which involves our model's forward function, which we defined up here when we built our model. The forward pass runs through this code here. So let's just write that. So in our case, because we're training, I'm just going to write here. This is training. We're going to see .eval later on. We'll talk about that when it comes. Let's do the forward pass. So the forward pass, we want to pass data through our model's forward method. We can do this quite simply by going ypred, so y predictions, because remember, we're trying to use, our ideal model is using x test to predict y test on our test data set. We make predictions on our test data set. We learn on our training data set. So we're passing, just going to get rid of that because we don't need that. So we're passing our model xtrain, and model 0 is going to be our current model. There we go. So we learn patterns on the training data to evaluate our model on the test data. Number 2, where are we at? So we have to calculate the loss. Now, in a previous video, we set up a loss function. So this is going to help us calculate the what. What kind of loss are we using? We want to calculate the MAE. So the difference or the distance between our red dot and a green dot. And the formula would be the same if we had 10,000 red dots and 10,000 green dots. We're calculating how far they are apart, and then we're taking the mean of that value. So let's go back here. So calculate the loss. And in our case, we're going to set loss equal to our loss function, which is L1 loss in PyTorch, but it is MAE. ypred, and ytrain. So we're calculating the difference between our model's predictions on the training data set and the ideal training values. And if you want to go into torch.nn loss functions, that's going to show you the order, because sometimes this confuses me too, what order the values go in here, but it goes prediction first, then labels. And I may be wrong there because I get confused here. My dyslexia kicks in, but I'm pretty sure it's predictions first, then actual labels. Do we have an example of where it's used? Yeah, input first, target next. So there we go. And truth be told, because it's mean absolute error, it shouldn't actually matter too much. But in the case of staying true to the documentation, let's do inputs first and then targets next for the rest of the course. Then we're going to go optimizer 0 grad. Haven't discussed this one, but that's okay. I'm going to write the code and then I'm going to discuss what it does. So what does this do? Actually, before we discuss this, I'm going to write these two steps because they kind of all work together, and it's a lot easier to discuss what optimizer 0 grad does in the context of having everything else. Perform back propagation on the loss with respect to the parameters of the model. Backpropagation is going to take the loss value, so loss backward. I always say backwards, but it's just backward. That's the code there. And then number 5 is step the optimizer. So perform gradient descent. So optimizer.step. Woohoo, look at us. We just wrote the 5 major steps of a training loop. Now let's discuss how all of these work together. So it's kind of strange, like the ordering of these. You might think, oh, what should I do the order? Typically the forward pass and the loss come straight up. Then there's a little bit of ambiguity around what order these have to come in, but the optimizer step should come after the backpropagation. So I just like to keep this order how it is because this works. Let's just keep it that way. But what happens here? Well, It also is a little bit confusing in the first iteration of the loop because we've got 0 grad. But what happens here is that the optimizer makes some calculations in how it should adjust model parameters with regards to the backpropagation of the loss. And so by default, how the optimizer changes will accumulate through the loop. So we have to 0 them above in step 3 for the next iteration of the loop. So a big long comment there, but what this is saying is, let's say we go through the loop and the optimizer chooses a value of 1. Change it by 1. And then it goes through a loop again. If we didn't 0 it, if we didn't take it to 0, because that's what it is doing, it's going 1 to 0, it would go, okay, next one, 2, 3, 4, 5, 6, 7, 8, all through the loop, right? Because we're looping here. If this was 10, it would accumulate the value that it's supposed to change 10 times. But we want it to start fresh each iteration of the loop. And now the reason why it accumulates, that's pretty deep in the PyTorch documentation. From my understanding, there's something to do with like efficiency of computing. If you find out what the exact reason is, I'd love to know. So we have to 0 it, then we perform backpropagation. If you recall, backpropagation is discussed in here. And then with optimizer step, we form gradient descent. So the beauty of PyTorch, this is the beauty of PyTorch, is that it will perform backpropagation. We're going to have a look at this in a second, and gradient descent for us. So to prevent this video from getting too long, I know we've just written code, but I would like you to practice writing a training loop yourself. Just write this code and then run it and see what happens. Actually, you can comment this out. We're going to write the testing loop in a second. So your extra curriculum for this video is to, 1, rewrite this training loop, is to, 2, sing the PyTorch optimization loop song. Let's go into here. If you want to remember the steps, well, I've got a song for you. This is the training loop song. We haven't discussed the test step, but maybe you could try this yourself. So, and this is an old version of the song, actually. I've got a new one for you. But let's sing this together. It's train time. So we do the forward pass, calculate the loss, optimize a 0 grad, loss backwards, optimize a step, step, step. Now you only have to call optimize a step once. This is just for jingle purposes. But for test time, let's test. With torch no grad, do the forward pass, calculate the loss, watch it go down, down, down. And that's from my Twitter. But this is a way that I help myself remember the steps that are going on in the code here. And if you want the video version of it, well, you're just going to have to search unofficial PyTorch optimization loop song. Oh, look at that. Who's that guy? Well, he looks pretty cool. So I'll let you check that out in your own time. But for now, go back through the training loop steps. I've got a colorful graphic coming up. In the next video, we're going to write the testing steps. And then we're going to go back one more time and talk about what's happening in each of them. And again, if you'd like some even more extra curriculum, don't forget the videos I've shown you on backpropagation and gradient descent. But for now, let's leave this video here. I'll see you in the next one. Friends, welcome back. In the last few videos, we've been discussing the steps in a training loop in PyTorch, and there's a fair bit going on. So in this video, we're going to step back through what we've done just to recap, and then we're going to get into testing. And it's nice and early where I am right now. The sun's about to come up. It's a very, very beautiful morning to be writing code. So let's jump in. We've got a little song here for what we're doing in the training steps. For an epoch in a range, call model.train, do the forward pass, calculate the loss, optimize a 0 grad, loss backward, optimize a step, step, step. That's the little jingle I use to remember the steps in here, because the first time you write it, there's a fair bit going on. But subsequent steps and subsequent times that you do write it, you'll start to memorize this, and even better, later on, we're going to put it into a function so that we can just call it over and over and over and over again. With that being said, let's jump in to a colorful slide, because that's a lot of code on the page. Let's add some color to it understand what's happening. That way you can refer to this and go, I see what's going on now. So for the loop, this is why it's called a training loop. We step through a number of epochs. One epoch is a single forward pass through the data. So pass the data through the model for a number of epochs. Epochs is a hyperparameter, which means you could set it to 100, you could set it to 1,000, you could set it to 1, as we're going to see later on in this video. We skip this step with the colors, but we put the model in, we call model.train. This is the default mode that the model is in. Essentially, it sets up a whole bunch of settings behind the scenes in our model parameters so that they can track the gradients and do a whole bunch of learning behind the scenes with these functions down here. PyTorch does a lot of this for us. So the next step is the forward pass. We perform a forward pass on the training data in the training loop. This is an important note. In the training loop is where the model learns patterns on the training data. Whereas in the testing loop, we haven't got to that yet, is where we evaluate the patterns that our model has learned or the parameters that our model has learned on unseen data. So we pass the data through the model. This will perform the forward method located within the model object. So because we created a model object, you can actually call your models whatever you want, but it's good practice you'll often see it just called model. And if you remember, we'll go back to the code. We created a forward method in our model up here, which is this. Because our linear regression model class subclasses nn.module, we need to create our own custom forward method. So that's why it's called a forward pass, is because not only does it, well, the technical term is forward propagation. So if we have a look at a neural network picture, forward propagation just means going through the network from the input to the output. There's a thing called back propagation, which we're going to discuss in a second, which happens when we call loss.backward, which is going backward through the model. But let's return to our colorful slide. We've done the forward pass. Call a forward method, which performs some calculation on the data we pass it. Next is we calculate the loss value, how wrong the model's predictions are. And this will depend on what loss function you use, what kind of predictions your model is outputting, and what kind of true values you have. But that's what we're doing. Here we're comparing our model's predictions on the training data to what they should ideally be. And these will be the training labels. The next step, we zero the optimizer gradients. So why do we do this? Well, it's a little confusing for the first epoch in the loop, but as we get down to optimizer.step here, the gradients that the optimizer calculates accumulate over time, so that for each epoch, for each loop step, we want them to go back to 0. And now the exact reason behind why the optimizer accumulates gradients is buried somewhere within the PyTorch documentation. I'm not sure of the exact reason. From memory, it's because of compute optimization. It just adds them up in case you wanted to know what they were. But if you find out exactly, I'd love to know. Next step is to perform back propagation on the loss function. That's what we're calling loss.backward. Now, back propagation is we compute the gradient of every parameter with requires grad equals true. And if you recall, we go back to our code. We've set requires grad equals true for our parameters. Now, the reason we've set requires grad equals true is not only so back propagation can be performed on it, but let me show you what the gradients look like. So let's go loss function curve. That's a good idea. So we're looking for some sort of convex curve here. There we go, L2 loss. We're using L1 loss at the moment. Is there a better one here? All we need is just a nice looking curve. Here we go. So this is why we keep track of the gradients. Behind the scenes, PyTorch is going to create some sort of curve for all of our parameters that looks like this. Now, this is just a 2D plot. So the reason why we're just using an example from Google Images is 1, because you're going to spend a lot of your time Googling different things. And 2, in practice, when you have your own custom neural networks, right now we only have 2 parameters. So it's quite easy to visualize a loss function curve like this. But when you have, say, 10 million parameters, you basically can't visualize what's going on. And so PyTorch, again, will take care of these things behind the scenes. But what it's doing is when we say requires grad, PyTorch is going to track the gradients of each of our parameters. And so what we're trying to do here with backpropagation and subsequently gradient descent is calculate where the lowest point is. Because this is a loss function, this is MSE loss, we could trade this out to be MAE loss in our case, or L1 loss for our specific problem. But this is some sort of parameter, and we calculate the gradients because what is the gradient? Let's have a look. What is a gradient? A gradient is an inclined part of a road or railway. No, we want it in machine learning. What's it going to give us? In machine learning, a gradient is a derivative of a function that has more than one input variable. Okay, let's dive in a little deeper. See, here's some beautiful loss landscapes. We're trying to get to the bottom of here. This is what gradient descent is all about. So, oh, there we go. So this is a cost function, which is also a loss function. We start with a random initial variable. What have we done? We've started with a random initial variable. Right, okay, and then we take a learning step, beautiful. This is W, so this could be our weight parameter. Okay, we're connecting the dots here. This is exciting. We've got a lot of tabs here, but that's all right. We'll bring this all together in a second. And what we're trying to do is come to the minimum. Now, why do we need to calculate the gradients? Well, the gradient is what? Oh, value of weight. Here we go. This is even better. I love Google Images. So this is our loss. And this is the value of a weight. So we calculate the gradients. Why? Because the gradient is the slope of a line or the steepness. And so if we calculate the gradient here and we find that it's really steep right up the top of this incline, we might head in the opposite direction to that gradient. That's what gradient descent is. And so if we go down here, now what are these step points? There's a little thing that I wrote down in the last video, at the end of the last video, I haven't told you about yet, but I was waiting for a moment like this. And if you recall, I said kind of all of these three steps, optimize a zero grad, loss backward, optimize a step are all together. So we calculate the gradients because we want to head in the opposite direction of that gradient to get to a gradient value of 0. And if we get to a gradient value of 0 with a loss function, well then the loss is also 0. So that's why we keep track of the gradient with requires grad equals true. And again, PyTorch does a lot of this behind the scenes. And if you want to dig more into what's going on here, I'm going to show you some extra resources for backpropagation, which is calculating this gradient curve here, and gradient descent, which is finding the bottom of it towards the end of this video. And again, if we started over this side, we would just go in the opposite direction of this. So maybe this is a positive gradient here, and we just go in the opposite direction here. We want to get to the bottom. That is the main point of gradient descent. And so if we come back, I said, just keep this step size in mind here. If we come back to where we created our loss function and optimizer, I put a little tidbit here for the optimizer because we've written a lot of code and we haven't really discussed what's going on, but I like to do things on the fly as we need them. So inside our optimizer, we'll have main two parameters, which is params. So the model parameters you'd like to optimize. Params equals model 0.parameters in our case. And PyTorch is going to create something similar to this curve, not visually, but just mathematically behind the scenes for every parameter. Now, this is a value of weight, so this would just be potentially the weight parameter of our network. But again, if you have 10 million parameters, there's no way you could just create all of these curves yourself. That's the beauty of PyTorch. It's doing this behind the scenes through a mechanism called Torch AutoGrad, which is auto gradient calculation. And there's beautiful documentation on this. If you'd like to read more on how it works, please go through that. But essentially behind the scenes, it's doing a lot of this for us for each parameter. That's the optimizer. Then within the optimizer, once we've told it what parameters to optimize, we have the learning rate. So the learning rate is another hyperparameter that defines how big or small the optimizer changes the parameters with each step. So a small learning rate results in small changes, whereas a large learning rate is in large changes. And so if we look at this curve here, we might at the beginning start with large steps so we can get closer and closer to the bottom. But then as we get closer and closer to the bottom, to prevent stepping over to this side of the curve, we might do smaller and smaller steps. And the optimizer in PyTorch, there are optimizers that do that for us, but there is also another concept called learning rate scheduling, which is, again, something if you would like to look up and do more. But learning rate scheduling essentially says, hey, maybe start with some big steps, and then as we get closer and closer to the bottom, reduce how big the steps are that we take. Because if you've ever seen a coin at back of couch, this is my favorite analogy for this. If you've ever tried to reach a coin at the back of a couch, like this excited young chap, if you're reaching towards the back of the couch, you take quite big steps as you, say your arm was over here, you would take quite big steps until you get to about here, and then the closer you get to the coin, the smaller and smaller your steps are. Otherwise, what's going to happen? The coin's going to be lost, or if you took 2 small steps, you'd never get to the coin. It would take forever to get there. So that's the concept of the learning rate. If you take 2 big steps, you're going to just end up over here. If you take 2 small steps, it's going to take you forever to get to the bottom here. And this bottom point is called convergence. That's another term you're going to come across. I know I'm throwing a lot of different terms at you, but that's the whole concept of the learning rate. How big is your step down here in gradient descent? Gradient descent is this. Backpropagation is calculating these derivative curves or the gradient curves for each of the parameters in our model. So let's get out of here. We'll go back to our training steps. Where were we? I think we're up to backpropagation. Have we done backward? Yes. So the backpropagation is where we do the backward step. So the forward pass, forward propagation, go from input to output. Backpropagation, we take the gradients of the loss function with respect to each parameter in our model by going backwards. That's what happens when we call loss.backward. PyTorch does that for us behind the scenes. And then finally, step number 5 is step the optimizer. We've kind of discussed that. As I said, if we take a step, let's get our loss curve back up. Loss function curve, doesn't really matter what curve we use. The optimizer step is taking a step this way to try and optimize the parameters so that we can get down to the bottom here. And I also just noted here that you can turn all of this into a function, so we don't necessarily have to remember to write these every single time. The ordering of this, you'll want to do the forward pass first, and then calculate the loss, because you can't calculate the loss unless you do the forward pass. I like this ordering here of these 3 as well, but you also want to do the optimizer step after the loss backward. So this is my favorite ordering. It works. If you like this ordering, you can take that as well. With that being said, I think this video has gotten long enough. In the next video, I'd like to step through this training loop 1 epoch at a time so that we can see, I know I've just thrown a lot of words at you that this optimizer is going to try and optimize our parameters each step, but let's see that in action, how our parameters of our model actually change every time we go through each one of these steps. So I'll see you in the next video. Let's step through our model. Welcome back. Now we've spent a fair bit of time on the training loop and the testing loop. Well, we haven't even got to that yet, but there's a reason behind this, because this is possibly one of the most important things, aside from getting your data ready, which we're going to see later on in PyTorch deep learning, is writing the training loop, because this is literally like how your model learns patterns and data. So that's why we're spending a fair bit of time on here. And we'll get to the testing loop, because that's how you evaluate the patterns that your model has learned from data, which is just as important as learning the patterns themselves. And following on from the last couple of videos, I've just linked some YouTube videos that I would recommend for extra curriculum for backpropagation, which is what happens when we call loss.backward down here. And for the optimizer step, gradient descent is what's happening there. So I've linked some extra resources for what's going on behind the scenes there from a mathematical point of view. Remember, this course focuses on writing PyTorch code, but if you'd like to dive into what math PyTorch is triggering behind the scenes, I'd highly recommend these 2 videos. And I've also added a note here as to which loss function and optimizer should I use, which is a very valid question. And again, it's another one of those things that's going to be problem specific. But with experience over time, you work with machine learning problems, you write a lot of code, you get an idea of what works and what doesn't with your particular problem set. For example, like a regression problem like ours, regression is again predicting a number. We use MAE loss, which PyTorch causes L1 loss. You could also use MSE loss, and an optimizer like Torch Optim stochastic gradient descent will suffice. But for classification, you might want to look into a binary classification, a binary cross-entropy loss, but we'll look at a classification problem later on in the course. For now, I'd like to demonstrate what's going on in the steps here. So let's go model 0. Let's look up the state dict and see what the parameters are for now. Now, they aren't the original ones, I don't think. Let's reinstantiate our model so we get new parameters. Yeah, we recreated it here. I might just get rid of that. So we'll rerun our model code, rerun model state dict, and we will create an instance of our model and just make sure your parameters should be something similar to this. If it's not exactly like that, it doesn't matter, but yeah, I'm just going to showcase. You'll see on my screen what's going on anyway. State dict 3367 for the weight and 01288 for the bias. And again, I can't stress enough, we've only got 2 parameters for our model and we've set them ourselves. Future models that you build and later ones in the course will have much, much more, and we won't actually explicitly set any of them ourselves. We'll check out some predictions. They're going to be terrible because we're using random parameters to begin with, but we'll set up a new loss function and an optimizer. Optimizer is going to optimize our model 0 parameters, the weight and bias. The learning rate is 0.01, which is a relatively large step. That would be a bit smaller. Remember, the larger the learning rate, the bigger the step, the more the optimizer will try to change these parameters every step. But let's stop talking about it. Let's see it in action. I've set a manual seed here too, by the way, because the optimizer's steps are going to be quite random as well, depending on how the model's predictions go. But this is just to try and make it as reproducible as possible. So keep this in mind. If you get different values to what we're going to output here, from my screen to your screen, don't worry too much. What's more important is the direction they're going. So ideally, we're moving these values here. This is from we did one epoch before. We're moving these values closer to the true values. And in practice, you won't necessarily know what the true values are. But that's where evaluation of your model comes in. We're going to cover that when we write a testing loop. So let's run one epoch. Now, I'm going to keep that down there. Watch what happens. We've done one epoch, just a single epoch. We've done the forward pass, we've calculated the loss, we've done optimizer 0 grad, we've performed back propagation, and we've stepped the optimizer. What does stepping the optimizer do? It updates our model parameters to try and get them further closer towards the weight and bias. If it does that, the loss will be closer to 0. That's what it's trying to do. How about we print out the loss at the same time? Print loss and the loss. Let's take another step. So the loss is 0.301. Now we check the weights and the bias. We've changed again. 3.445.1488. We go again. Oh, the loss is going down. Check it. Hey, look at that. The values are getting closer to where they should be, if ever so slightly. Loss went down again. Oh my goodness, this is so amazing. Look, we're training our, let's print this out in the same cell. Print out model state dict. We're training our first machine learning model here, people. This is very exciting, even if it's only step by step and it's only a small model. This is very important. Loss is going down again. Values are getting closer to where they should be. Again, we won't really know where they should be in real problems, but for now we do. So let's just get excited. The real way to sort of measure your model's progress in practice is a lower loss value. Remember, lower is better. A loss value measures how wrong your model is. We're going down. We're going in the right direction. So that's what I meant by as long as your values are going in the similar direction, so down, we're writing similar code here. But if your values are slightly different in terms of the exact numbers, don't worry too much, because that's inherent to the randomness of machine learning, because the steps that the optimizer are taking are inherently random, but they're sort of pushed in a direction. So we're doing gradient descent here. This is beautiful. How low can we get the loss? How about we try to get to 0.1? Look at that, we're getting close to 0.1. And then, I mean, we don't have to do this hand by hand. Oh, the bias is getting close to where it exactly should be. We're below 0.1, beautiful. So that was only about, say, 10 passes through the data, but now you're seeing it in practice. You're seeing it happen. You're seeing gradient descent. Let's go, gradient descent, work in action. We got images. This is what's happening. We've got our cost function. J is another term for cost function, which is also our loss function. We start with an initial weight. What have we done? We started with an initial weight, this value here. And what are we doing? We've measured the gradient. PyTorch has done that behind the scenes for us. Thank you, PyTorch. And we're taking steps towards the minimum. That's what we're trying to do. If we minimize the gradient of our weight, we minimize the cost function, which is also a loss function. We could keep going here for hours and get as low as we want. But my challenge for you, or actually, how about we make some predictions with our model we've got right now? Let's make some predictions. So with torch.inference mode, we'll make some predictions together, and then I'm going to set you a challenge. How about you run this code here for 100 epochs after this video, and then you make some predictions and see how that goes. So ypreds, remember how poor our predictions are? Ypreds new equals, we just do the forward pass here, model 0 on the test data. Let's just remind ourselves quickly of how poor our previous predictions were. Plot predictions, predictions equals y. Do we still have this saved? Ypreds. Hopefully this is still saved. There we go, shocking predictions. But we've just done 10 or so epochs, so 10 or so training steps. Have our predictions, do they look any better? Let's run this. We'll copy this code. You know my rule, I don't really like to copy code, but in this case, I just want to exemplify a point. I like to write all the code myself. What do we got? Ypreds new. Look at that! Look at that! We are moving our predictions closer. The red dot's closer to the green dots. This is what's happening. We're reducing the loss. In other words, we're reducing the difference between our model's predictions and our ideal outcomes through the power of backpropagation and gradient descent. So this is super exciting. We're training our first machine learning model. My challenge to you is to run this code here, change epochs to 100, see how low you can get this loss value, and run some predictions, plot them, and I think it's time to start testing. So give that a go yourself, and then we'll write some testing code in the next video. I'll see you there. Welcome back. In the last video, we did something super exciting. We saw our loss go down. So the loss is, remember, how different our model's predictions are to what we'd ideally like them. And we saw our model update its parameters through the power of backpropagation and gradient descent, all taken care of behind the scenes for us by PyTorch. So thank you, PyTorch. And again, if you'd like some extra resources on what's actually happening from a math perspective for backpropagation and gradient descent, I would refer to you to these. Otherwise, this is also how I learn about things. Gradient descent. There we go. How does gradient descent work? And then we've got backpropagation. And just to reiterate, I am doing this, just Googling these things, because that's what you're going to do in practice. You're going to come across a lot of different things that aren't covered in this course. And this is seriously what I do day to day as a machine learning engineer if I don't know what's going on. I just go to Google, read, watch a video, write some code, and then I build my own intuition for it. But with that being said, I also issued you the challenge of trying to run this training code for 100 epochs. Did you give that a go? I hope you did. And how low did your loss value get? Did the weights and bias get anywhere close to where they should have been? How do the predictions look? Now, I'm going to save that for later on, running this code for 100 epochs. For now, let's write some testing code. And just a note, you don't necessarily have to write the training and testing loop together. You can functionize them, which we will be doing later on. But for the sake of this intuition building and code practicing and first time we're writing this code together, I'm going to write them together. So testing code, we call model.eval. What does this do? So this turns off different settings in the model not needed for evaluation/testing. This can be a little confusing to remember when you're writing testing code, but we're going to do it a few times until it's habit. So just make it a habit. If you're training your model, call model.train to make sure it's in training mode. If you're testing or evaluating your model, so that's what eval stands for, evaluate, call model.eval. So it turns off different settings in the model not needed for evaluations or testing. This is things like dropout. We haven't seen what dropout is, /batch norm layers. But if we go into torch.nn, I'm sure you'll come across these things in your future machine learning endeavors. So dropout layers, there we go. And batch norm, do we have batch? Batch norm, there we go. If you'd like to work out what they are, feel free to check out the documentation. Just take it from me for now that model.eval turns off different settings not needed for evaluation and testing. Then we set up with torch.inference mode. Inference mode. So what does this do? Let's write down here. So this turns off gradient tracking. So as we discussed, if we have parameters in our model, and it turns off actually a few more things, and a couple more things behind the scenes, these are things, again, not needed for testing. So we discussed that if parameters in our model have requires grad equals true, which is the default for many different parameters in PyTorch, PyTorch will, behind the scenes, keep track of the gradients of our model and use them in loss.backward and optimizer step for backpropagation and gradient descent. However, we only need those two, backpropagation and gradient descent, during training because that is when our model is learning. When we are testing, we are just evaluating the parameters, the patterns that our model has learned on the training data set. So we don't need to do any learning when we're testing. So we turn off the things that we don't need. And is this going to have the correct spacing for me? I'm not sure. We'll find out. So we still do the forward pass in testing mode. Do the forward pass. And if you want to look up torch inference mode, just go torch inference mode. There's a great tweet about it that PyTorch did, which explains what's happening. I think we've covered this before, but yeah. Want to make your inference code in PyTorch run faster? Here's a quick thread on doing exactly that. So inference mode is torch no grad. Again, you might see torch no grad. I think I'll write that down just to let you know. But here's what's happening behind the scenes. A lot of optimization code, which is beautiful. This is why we're using PyTorch, so that our code runs nice and fast. Then we go there. You may also see with torch.nograd in older PyTorch code. It does similar things, but inference mode is the faster way of doing things, according to the thread and according to, there's a blog post attached to there as well, I believe. So you may also see torch.nograd in older PyTorch code, which would be valid, but again, inference mode is the better way of doing things. So do forward pass. So let's get our model. We want to create test predictions here. So we're going to go model 0. There's a lot of code going on here, but I'm going to just step by step it in a second. We'll go back through it all. And then number 2 is calculate the loss. Now, we're doing the test predictions here. Calculate the loss. Test predictions with model 0. So now we want to calculate the what? We want to calculate the test loss. So this will be our loss function, the difference between the test pred and the test labels. That's important. So for testing, we're working with test data. For training, we're working with training data. Model learns patterns on the training data, and it evaluates those patterns that it's learned, the different parameters on the testing data. Data it has never seen before. Just like in a university course, you'd study the course materials, which is the training data, and you'd evaluate your knowledge on materials you'd hopefully never seen before, unless you sort of were friends with your professor and they gave you the exam before the actual exam. That would be cheating, right? So that's a very important point for the test data set. Don't let your model see the test data set before you evaluate on it. Otherwise, you'll get poor results. And that's print out what's happening. Epoch, we're going to go epoch, and then I will introduce you to my little jingle to remember all of these steps, because there's a lot going on. Don't you worry. I know there's a lot going on. But again, with practice, we're going to know what's happening here like it's the back of our hand. All right. So do we need this? Oh yeah, we could say that. Oh no, we don't need test here. Loss. This is loss, not test. Print out what's happening. Okay. And we don't actually need to do this every epoch. We could just go say if epoch divided by 10 equals 0, print out what's happening. Let's do that. Rather than clutter everything up, print it out, and we'll print out this. So let's just step through what's happening. We've got 100 epochs. That's what we're about to run. 100 epochs. Our model is trained for about 10 so far, so it's got a good base. Maybe we'll just get rid of that base. Start a new instance of our model. So we'll come right back down. So our model is back to randomly initialized parameters, but of course, randomly initialized, flavored with a random seed of 42. Lovely, lovely. And so we've got our training code here. We've discussed what's happening there. Now we've got our testing code. We call model.eval, which turns off different settings in the model not needed for evaluation/testing. We call with torch inference mode context manager, which turns off gradient tracking and a couple more things behind the scenes to make our code faster. We do the forward pass, we do the test predictions, we pass our model the test data, the test features to calculate the test predictions. Then we calculate the loss using our loss function. We can use the same loss function that we used for the training data, and it's called the test loss because it's on the test data set. And then we print out what's happening because we want to know what's happening while our model's training. We don't necessarily have to do this, but the beauty of PyTorch is you can use basic Python printing statements to see what's happening with your model. And so because we're doing 100 epochs, we don't want to clutter up everything here, so we'll just print out what's happening every 10th epoch. Again, you can customize this as much as you like what's printing out here. This is just one example. If you had other metrics here, such as calculating model accuracy, we might see that later on, hint, hint. We might print out our model accuracy. So this is very exciting. Are you ready to run 100 epochs? How low do you think our loss can go? This loss was after about 10, so let's just save this here. Let's give it a go. Ready? 3, 2, 1, let's run. Oh my goodness, look at that. Weights. Here we go. Every 10 epochs, we're printing out what's happening. So the 0th epoch, we started with loss is 312. Look at it go down. Yes, that's what we want. And are our weights and bias, are they moving towards our ideal weight and bias values of 0.7 and 0.3? Yes, they're moving in the right direction here. The loss is going down. Epoch 20, wonderful. Epoch 30, even better. 40, 50, going down, down, down. Yes, this is what we want. This is what we want. Now, we're predicting a straight line here. Look how low the loss gets. After 100 epochs, we've got about 3 times less than what we had before. And then we got these values are quite close to where they should be. 05629, 03573. We'll make some predictions. What do they look like? ypreds new. This is the original predictions with random values. And if we make ypreds new, look how close it is after 100 epochs. Now, do we print out the test loss? Oh no, we're printing out loss as well. Let's get rid of that. I think that's this statement here. Our code would have been much cleaner if we didn't have that, but that's all right. Life goes on. So our test loss, because this is the test predictions that we're making, is not as low as our training loss. I wonder how we could get that lower. What do you think we could do? We just trained it for longer, and what happened? How do you think you could get these red dots to line up with these green dots? Do you think you could? So that's my challenge to you for the next video. Think of something that you could do to get these red dots to match up with these green dots. Maybe train for longer. How do you think you could do that? So give that a shot, and I'll see you in the next video. We'll review what our testing code is doing. I'll see you there. Welcome back. In the last video, we did something super exciting. We trained our model for 100 epochs and look how good the predictions got. But I finished it off with challenging you to see if you could align the red dots with the green dots. And it's okay if you're not sure how the best way to do that. That's what we're here for. We're here to learn what are the best way to do these things together. But you might have had the idea of potentially training the model for a little bit longer. So how could we do that? Well, we could just rerun this code. So the model's going to remember the parameters that it has from what we've done here. And if we rerun it, well, it's going to start from where it finished off, which is already pretty good for our data set. And then it's going to try and improve them even more. This is, I can't stress enough, like what we are doing here is going to be very similar throughout the entire rest of the course for training more and more models. So this step that we've done here for training our model and evaluating it is seriously like the fundamental steps of deep learning with PyTorch, is training and evaluating a model. And we've just done it. Although, albeit to predict some red dots and green dots, that's all right. So let's try to line them up, hey? Red dots onto green dots. I reckon if we train it for another 100 epochs, we should get pretty darn close. You ready? 3, 2, 1. I'm going to run this cell again. Runs really quick because our data is nice and simple, but look at this. Last, we start at 0244. Where do we get down to? 008. Oh my goodness. So we've improved it by another 3x or so. And now this is where our models got really good. On the test loss, we've gone from 0564 and we've gone down to 005. So almost 10x improvement there. And so we make some more predictions. What are our model parameters? Remember the ideal ones here. We won't necessarily know them in practice, but because we're working with a simple data set, we know what the ideal parameters are. Model 0 state dig weights. These are what they previously were. What are they going to change to? Oh, would you look at that? 06990. Now, again, if yours are very slightly different to mine, don't worry too much. That is the inherent randomness of machine learning and deep learning. Even though we set a manual seed, it may be slightly different. The direction is more important. So if your number here is not exactly what mine is, it should still be quite close to 0.7. And the same thing with this one. If it's not exactly what mine is, don't worry too much. The same with all of these loss values as well. The direction is more important. So we're pretty darn close. How do these predictions look? Remember, these are the original ones. We started with random, and now we've trained a model. Oh, so close. So close to being exactly that. So a little bit off, but that's all right. We could tweak a few things to improve this, but I think that's well and truly enough for this example purpose. You see what's happened. Of course, we could just create a model and set the parameters ourselves manually, but where would be the fun in that? We just wrote some machine learning code to do it for us through the power of backpropagation and gradient descent. Now, in the last video, we wrote the testing loop. We discussed a few of the steps here, but now let's go over it with a colorful slide, hey? Because, I mean, code on a page is nice, but colors are even nicer. Oh, we haven't done this. We might set up this in this video too. But let's just discuss what's going on. Create an empty list for storing useful value. So this is helpful for tracking model progress. How about we just do this right now, hey? We'll go here and we'll go, so what did we have? Epoch count equals that. And then we'll go loss values. So why do we keep track of these? It's because if we want to monitor our model's progress, this is called tracking experiments. So track different values. If we wanted to try and improve upon our current model with a future model, so our current results, such as this, if we wanted to try and improve upon it, we might build an entire another model and we might train it in a different setup. We might use a different learning rate. We might use a whole bunch of different settings. But we track the values so that we can compare future experiments to past experiments, like the brilliant scientists that we are. And so where could we use these lists? Well, we're calculating the loss here, and we're calculating the test loss here. So maybe we each time append what's going on here as we do a status update. So epoch count dot append, and we're going to go the current epoch, and then we'll go loss values dot append the current loss value, and then we will do test loss values dot append the current test loss values. Wonderful. And now let's reinstantiate our model so that it starts from fresh. So this is just create another instance. So we're just going to reinitialize our model parameters to start from 0. If we wanted to, we could functionize all of this so we don't have to go right back up to the top of the code. But just for demo purposes, we're doing it how we're doing it. And I'm going to run this for, let's say 200 epochs, because that's what we ended up doing, right? We ran it for 200 epochs because we did 100 epochs twice. And I want to show you something beautiful, one of the most beautiful sites in machine learning. So there we go, we run it for 200 epochs. We start with a fairly high training loss value and a fairly high test loss value. So remember, what is our loss value? It's MAE. So if we go back, yeah, this is what we're measuring for loss. So this means for the test loss, on average, each of our dot points here, the red predictions, are 0.481. That's the average distance between each dot point. And then ideally, what are we doing? We're trying to minimize this distance. That's the MAE. So the mean absolute error. And we get it right down to 0.05. And if we make predictions, what do we have here? We get very close to the ideal weight and bias. Make our predictions. Have a look at the new predictions. Yeah, very small distance here. Beautiful. That's a low loss value. Ideally, they'd line up, but we've got as close as we can for now. So this is one of the most beautiful sites in machine learning. So plot the loss curves. So let's make a plot, because what were we doing? We were tracking the value of epoch count, loss values, and test loss values. Let's have a look at what these all look like. So epoch count goes up, loss values ideally go down. So we'll get rid of that. We're going to create a plot, plt.plot. We're going to step back through the test loop in a second with some colorful slides. Label equals train loss. And then we're going to go plot. You might be able to tell what's going on here. Test loss values. We're going to visualize it because that's the Data Explorer's motto, right? Is visualize, visualize, visualize. This is equals... See, Colab does this autocorrect that doesn't really work very well. And I don't know when it does it and why it does it. Have we got... Oh no, we didn't say loss value. So that's a good autocorrect. Thank you, Colab. So training and loss and test loss curves. So this is another term you're going to come across often, is a loss curve. Now you might be able to think about a loss curve. If we're doing a loss curve and it's starting at the start of training, what do we want that curve to do? What do we want our loss value to do? We want it to go down. So what should an ideal loss curve look like? Well, we're about to see a couple. Let's have a look. Oh, what do we got wrong? We need to, turn it into NumPy. Is this what we're getting wrong? So why is this wrong? Loss values, why are we getting an issue? Test loss values. It's because they're all tensor values. So I think we should, I might change this to NumPy. Oh, can I just do that? If I just call this as a NumPy array, we're going to try and fix this on the fly, people. NumPy array. Will this turn this into a NumPy array? Let's see if we get NumPy. We're figuring these things out together. NumPy as NumPy. Because matplotlib works with NumPy. Yeah, there we go. So can we do loss values? Maybe I'm going to try one thing, torch.tensor. Loss values, and then call CPU.numpy. See what happens here. There we go. Okay, so let's just copy this. So what we're doing here is our loss values are still on PyTorch, and they can't be because matplotlib works with NumPy. And so what we're doing here is we're converting our loss values of the training loss to NumPy. And if you recall from the fundamentals section, we call CPU and NumPy. I wonder if we can just do straight up NumPy. Because we're not working on the... Yeah, okay. We don't need CPU because we're not working on the GPU yet. But we might need that later on. Will this work? Beautiful. There we go. One of the most beautiful sights in machine learning is a declining loss curve. So this is how we keep track of our experiments. Or one way. Quite rudimentary. We'd like to automate this later on. But I'm just showing you one way to keep track of what's happening. So the training loss curve is going down here. The training loss starts at 0.3 and then it goes right down. The beautiful thing is they match up. If there was a too big a distance behind the train loss and the test loss, or sorry, between, then we're running into some problems. But if they match up closely at some point, that means our model is converging and the loss is getting as close to zero as it possibly can. If we trained for longer, maybe the loss will go almost basically to zero. But that's an experiment I'll leave you to try, to train that model for longer. Let's just step back through our testing loop to finish off this video. So we did that. We created empty lists for strong useful values, storing useful values, strong useful values. Told the model what we want to evaluate, or that we want to evaluate. So we put it in an evaluation mode. It turns off functionality used for training, but not evaluation, such as dropout and batch normalization layers. If you want to learn more about them, you can look them up in the documentation. Turn on torch inference mode. So this is for faster performance. So we don't necessarily need this, but it's good practice. So I'm going to say that, yes, turn on torch inference mode. So this disables functionality such as gradient tracking for inference. Gradient tracking is not needed for inference, only for training. Now we pass the test data through the model. So this will call the model's implemented forward method. The forward pass is the exact same as what we did in the training loop, except we're doing it on the test data. So big notion there, training loop, training data, testing loop, testing data. Then we calculate the test loss value, how wrong the model's predictions are on the test data set, and of course, lower is better. Then finally, we print out what's happening so we can keep track of what's going on during training. We don't necessarily have to do this. You can customize this print value to print out almost whatever you want because PyTorch is basically very beautifully interactive with pure Python. And then we keep track of the values of what's going on in epochs and train loss and test loss. We could keep track of other values here, but for now we're just going, okay, what's the loss value at a particular epoch for the training set and for the test set? And of course, all of this could be put into a function, and that way we won't have to remember these steps off by heart. But the reason why we've spent so much time on this is because we're going to be using this training and test functionality for all of the models that we build throughout this course. So, give yourself a pat on the back for getting through all of these videos. We've written a lot of code, we've discussed a lot of steps, but if you'd like a song to remember what's happening, let's finish this video off with my unofficial PyTorch optimization loop song. So, for an epoch in a range, call model.train, do the forward pass, calculate the loss, optimize a zero grad, loss backward, optimize a step, step, step. Note you only have to call this once, but now let's test. Call model.eval with torch inference mode, do the forward pass, calculate the loss, and then the real song goes for another epoch, because you keep going back through. But we finish off with print out what's happening. And then, of course, we evaluate what's going on. With that being said, it's time to move on to another thing. But if you'd like to review what's happening, please, please, please try to run this code for yourself again and check out the slides and also check out the extra curriculum. Oh, by the way, if you want a link to all of the extra curriculum, just go to the book version of the course and it's all going to be in here. So that's there ready to go. Everything I link as extra curriculum will be in the extra curriculum of each chapter. I'll see you in the next video. Welcome back. In the last video, we saw how to train our model and evaluate it by not only looking at the loss metrics and the loss curves, but we also plotted our predictions and we compared them. Hey, have a go at these random predictions. Quite terrible. But then we trained a model using the power of backpropagation and gradient descent, and now look at our predictions. They're almost exactly where we want them to be. And so you might be thinking, well, we've trained this model and it took us a while to write all this code to get some good predictions. How might we run that model again? So I've taken a little break after the last video, but now I've come back and you might notice that my Google Colab notebook has disconnected. So what does this mean? If I was to run this, is it going to work? I'm going to connect to a new Google Colab instance, but will we have all of the code that we've run above? You might have already experienced this if you took a break before and came back to the videos. So plot predictions is no longer defined. And do you know what that means? That means that our model is also no longer defined. So we would have lost our model. We would have lost all of that effort of training. Now, luckily, we didn't train the model for too long, so we can just go runtime, run all, and it's going to rerun all of the previous cells and be quite quick because we're working with a small data set and using a small model. But we've been through all of this code. Oh, what have we got wrong here? Model 0 state dict. Oh, that's all right. This is good. We're finding errors. So if you want to as well, you can just go run after. It's going to run all of the cells after. Beautiful. And we come back down. There's our model training. We're getting very similar values to what we got before. There's the loss curves. Beautiful. Still going. Okay, now our predictions are back because we've rerun all the cells and we've got our model here. So what we might cover in this video is saving a model in PyTorch. Because if we're training a model and you get to a certain point, especially when you have a larger model, you probably want to save it and then reuse it in this particular notebook itself, or you might want to save it somewhere and send it to your friend so that your friend can try it out. Or you might want to use it in a week's time. And if Google Colab is disconnected, you might want to be able to load it back in somehow. So now let's see how we can save our models in PyTorch. So I'm going to write down here, there are 3 main methods you should know about for saving and loading models in PyTorch. Because of course, with saving comes loading. So we're going to, over the next 2 videos, discuss saving and loading. So one is torch.save. And as you might guess, this allows you to save a PyTorch object in Python's pickle format. So you may or may not be aware of Python pickle. There we go. Python object serialization. There we go. So we've got the pickle module implements binary protocols for serializing and deserializing a Python object. So serializing means, I understand it as saving, and deserializing means that is loading. So this is what PyTorch uses behind the scenes, which is from pure Python. So if we go back here in Python's pickle format, number 2 is torch.load, which you might be able to guess what that does as well. Allows you to load a saved PyTorch object. And number 3 is also very important, is torch.nn.module.loadStateDict. Now, what does this allow you to do? Well, this allows you to load a model's saved dictionary, or saved state dictionary. Yeah, that's what we'll call it. Saved state dictionary. Beautiful. And what's the model state dict? Well, let's have a look. Model0.stateDict. The beauty of PyTorch is that it stores a lot of your model's important parameters in just a simple Python dictionary. Now, it might not be that simple because our model, again, only has 2 parameters. In the future, you may be working with models with millions of parameters. So looking directly at the state dict may not be as simple as what we've got here. But the principle is still the same. It's still a dictionary that holds the state of your model. And so I've got these 3 methods. I want to show you where from, because this is going to be your extra curriculum, save and load models. Your extra curriculum for this video. If we go into here, this is a very, very, very important piece of PyTorch documentation, or maybe even a tutorial. So your extra curriculum for this video is to go through it. Here we go. We've got torch save, torch load, torch module state dict. That's where, or load state dict. That's where I've got the three things that we've just written down. And there's a fair few different pieces of information. So what is a state dict? So in PyTorch, the learnable parameters, i.e. the weights and biases of a torch NN module, which is our model. Remember, our model subclasses NN module are contained in the model's parameters. Accessed with model.parameters, a state dict is simply a Python dictionary object that maps each layer to its parameter tensor. That's what we've seen. And so then if we defined a model, we can initialize the model, and if we wanted to print the state dict, we can use that. The optimizer also has a state dict, so that's something to be aware of. You can go optimizer.stateDict, and then you get an output here. And this is our saving and loading model for inference. So inference, again, is making a prediction. That's probably what we want to do in the future at some point. For now, we've made predictions right within our notebook, but if we wanted to use our model outside of our notebook, say in an application or in another notebook that's not this one, you'll want to know how to save and load it. So the recommended way of saving and loading a PyTorch model is by saving its state dict. Now, there's another method down here, which is saving and loading the entire model. So your extracurricular for this lesson, we're going to go through the code to do this, but your extracurricular is to read all of the sections in here and then figure out what the pros and cons are of saving and loading the entire model versus saving and loading just the state dict. So that's a challenge for you for this video. I'm going to link this in here. And now let's write some code to save our model. So PyTorch, save and load code. Code tutorial plus extra curriculum. So if we go saving our PyTorch model. So what might we want? What do you think the save parameter takes? If we have torch.save, what do you think it takes inside it? Well, let's find out together, hey? So let's import pathlib. We're going to see why in a second. This is Python's module for dealing with writing file paths. So if we wanted to save something to, this is Google Colab's files section over here. But just remember, if we do save this from within Google Colab, the model will disappear if our Google Colab notebook instance disconnects. So I'll show you how to download it from Google Colab if you want. Google Colab also has a way, save from Google Colab to Google Drive, to save it to your Google Drive if you wanted to, but I'll leave you to look at that on your own if you like. So we're first going to create a model directory. So create models directory. So this is going to help us create a folder over here called models. And of course we could create this by hand by adding a new folder here somewhere, but I like to do it with code. So model path, we're going to set this to path, which is using the path library here to create us a path called models. Simple. We're just going to save all of our models to the models file. And then we're going to create model path. We're going to make that directory. Model path.mkdir for make directory. We're going to set parents to equals true. And we're also going to set exist OK equals to true. That means if it already existed, it won't throw us an error. It will try to create it, but if it already exists, it'll just recreate the parents directory or it'll leave it there. It won't error out on us. We're also going to create a model save path. This way, we can give our model a name. Right now, it's just model 0. We want to save it under some name to the models directory. So let's create the model name. Model name equals 01. I'm going to call it 01 for the section. That way, if we have more models later on in the course, we know which ones come from where. You might create your own naming convention. Model workflow, PyTorch workflow, model0.pth. And now, this is another important point. PyTorch objects usually have the extension .pth for PyTorch or .pt. So if we go in here and if we look up .pt, yeah, a common convention is to save models using either a .pt or .pth file extension. I'll let you choose which one you like. I like .pth. So if we go down here, .pth, they both result in the same thing. You just have to remember to make sure you write the write loading path, and write saving path. So now we're going to create our model save path, which is going to be our model path. And because we're using the path lib, we can use this syntax that we've got here, model path / model name. And then if we just print out model save path, what does this look like? There we go. So it creates us a POSIX path using the path lib library of models /o1 PyTorch workflow model 0.pth. We haven't saved our model there yet. It's just got the path that we want to save our model ready. So if we refresh this, we've got models over here. Do we have anything in there? No, we don't yet. So now is our step to save the model. So 3 is save the model state dict. Why are we saving the state dict? Because that's the recommended way of doing things. If we come up here, saving and loading the model for inference, save and load the state dict, which is recommended. We could also save the entire model, but that's part of your extra curriculum to look into that. So let's use some syntax. It's quite like this, torch.save, and then we pass it an object, and we pass it a path of where to save it. We already have a path. And good thing is we already have a model. So we just have to call this. Let's try it out. So let's go print f saving model to, and we'll put in the path here, model save path. I like to print out some things here and there, that way we know what's going on. And, oh, I don't need that capital A, do I? Getting a little bit trigger happy here with the typing. So torch.save, and we're going to pass in the object parameter here. And if we looked up torch save, we can go, what does this code take? So torch save object f, what is f? A file like object. Okay. Or a string or OS path like object. Beautiful, that's what we've got. A path like object containing a file name. So let's jump back into here. The object is what? It's our model 0.stateDict. That's what we're saving. And then the file path is model save path. You ready? Let's run this and see what happens. Beautiful. Saving model to models. So that's our model path, and there's our model there. So if we refresh this, what do we have over here? Wonderful. We've saved our trained model. So that means we could potentially, if we wanted to, you could download this file here. That's going to download it from Google Colab to your local machine. That's one way to do it. But there's also a guide here to save from Google Collaboratory to Google Drive. That way you could use it later on. So there's many different ways. The beauty of PyTorch is its flexibility. So now we've got a saved model. But let's just check using our ls command. We're going to check models. Yeah, let's just check models. This is going to check here. So this is list. Wonderful. There's our O1 PyTorch workflow model 0.pth. Now, of course, we've saved a model. How about we try loading it back in and seeing how it works? So if you want a challenge, read ahead in the documentation and try to use torch.load to bring our model back in. See what happens. I'll see you in the next video. Welcome back. In the last video, we wrote some code here to save our PyTorch model. I'm just going to X out of this, a couple of things that we don't need just to clear up the screen. And now we've got our .pth file, because remember, .pth or .pt is a common convention for saving a PyTorch model. We've got it saved there, and we didn't necessarily have to write all of this path style code, but this is just handy for later on if we wanted to functionize this and create it in, say, a save.py file over here, so that we could just call our save function and pass it in a file path where we want it to save, like a directory and a name, and then it'll save it exactly how we want it for later on. But now we've got a saved model. I issued a challenge of trying to load that model in. So do we have torch.load in here? Did you try that out? We've got a few options here. Wonderful, but we're using one of the first ones. So let's go back up here. If we wanted to check the documentation for torch.load, we've got this option here, load. What happens? Loads an object saved with torch.save from a file. Torch.load uses Python's unpickling facilities, but treats storages which underlie tensors specially. They are first deserialized on the CPU and then are moved to the device they were saved from. Wonderful. So this is moved to the device. If later on when we're using a GPU, this is just something to keep in mind. We'll see that when we start to use a CPU and a GPU. But for now, let's practice using the torch.load method and see how we can do it. So we'll come back here and we'll go loading a PyTorch model. And since just going to start writing here, since we saved our model's state dict, so just the dictionary of parameters from a model, rather than the entire model, we'll create a new instance of our model class and load the state dict. Load the saved state dict, that's better, state dict, into that. Now, this is just words on a page. Let's see this in action. So to load in a state dict, which is what we saved, we didn't save the entire model itself, which is one option. That's extra curriculum. But we saved just the model state dict. So if we remind ourselves what model0.stateDict looks like, we saved just this. So to load this in, we have to instantiate a new class or a new instance of our linear regression model class. So to load in a saved state dict, we have to instantiate a new instance of our model class. So let's call this loaded model 0. I like that. That way we can differentiate because it's still going to be the same parameters as model 0, but this way we know that this instance is the loaded version, not just the version we've been training before. So we'll create a new version of it here, linear regression model. This is just the code that we wrote above, linear regression model. And then we're going to load the saved state dict of model 0. And so this will update the new instance with updated parameters. So let's just check before we load it. We haven't written any code to actually load anything. What does loaded model 0, what does the state dict look like here? It won't have anything. It'll be initialized with what? Oh, loaded. That's what I called it. Loaded. See how it's initialized with random parameters? So essentially all we're doing when we load a state dictionary into our new instance of our model is that we're going, hey, take the saved state dict from this model and plug it into this. So let's see what happens when we do that. So loaded model 0. Remember how I said there's a method to also be aware of up here, which is torch_nn_module.load_state_dict. And because our model is a what? It's a subclass of torch.nn.module, so we can call load_state_dict on our model directly, or on our instance. So recall, linear regression model is a subclass of nn.module. So let's call in load_state_dict, and this is where we call the torch.load method. And then we pass it the model save path. Is that what we called it? Because torch.load, it takes in f. So what's f? A file like object, or a string, or an OS path like object. So that's why we created this path like object up here, model save path. So all we're doing here, we're creating a new instance, linear regression model, which is a subclass of nn.module. And then on that instance, we're calling in load_state_dict of torch.load model save path, because what's saved at the model save path? Our previous model's state dict, which is here. So if we run this, let's see what happens. All keys match successfully. That is beautiful. And so see the values here? Loaded state dict of model 0. Well, let's check the loaded version of that. We now have, wonderful, we have the exact same values as above, but there's a little way that we can test this. So how about we go make some predictions? So make some predictions just to make sure with our loaded model. So let's put it in eval mode, because when you make predictions, you want it in evaluation mode, so it goes a little bit faster. And we want to also use inference mode. So with torch.inference mode for making predictions, we want to write this, loaded model preds. We're going to make some predictions on the test data as well. So loaded model 0, we're going to forward pass on the x test data, and then we can have a look at the loaded model preds. Wonderful. And then to see if the two models are the same, we can compare loaded model preds with original model preds. So y preds, these should be equivalent. Equals loaded model preds. Do we have the same thing? False, false, false. What's going on here? Y preds. How much different are they? Oh, where's that happened? Have we made some model preds with this yet? So how about we make some model preds? This is troubleshooting on the fly, team. So let's go model0.eval and then with torch.inference mode. This is how we can check to see that our two models are actually equivalent. ypreds equals, I have a feeling ypreds actually saved somewhere else, equals model0, and then we pass it the x test data. And then we might move this above here and then have a look at what ypreds equals. Do we get the same output? Yes, we should. Wonderful. Okay, beautiful. So now we've covered saving and loading models, or specifically saving the models state dict. So we saved it here with this code, and then we loaded it back in with load state dict plus torch load, and then we checked to see by testing equivalence of the predictions of each of our models. So the original one that we trained here, model 0, and the loaded version of it here. So that's saving and loading a model in PyTorch. There are a few more things that we could cover, but I'm going to leave that for extra curriculum. We've covered the two main things, or the three main things. 1, 2, 3. If you'd like to read more, I'd highly encourage you to go through and read this tutorial here. But with that being said, we've covered a fair bit of ground over the last few videos. How about we do a few videos where we put everything together, just to reiterate what we've done. I think that'll be good practice. I'll see you in the next video. Welcome back. Over the past few videos, we've covered a whole bunch of ground in a PyTorch workflow. Starting with data, then building a model. Well, we split the data, then we built a model. We looked at the model building essentials. We checked the contents of our model. We made some predictions with a very poor model because it's based off random numbers. We spent a whole bunch of time figuring out how we could train a model. We figured out what the loss function is. We saw an optimizer. We wrote a training and test loop. We then learned how to save and load a model in PyTorch. So now I'd like to spend the next few videos putting all this together. We're not going to spend as much time on each step, but we're just going to have some practice together so that we can reiterate all the things that we've done. So putting it all together, let's go back through the steps above and see it all in one place. Wonderful. So we're going to start off with 6.1 and we'll go have a look at our workflow. So 6.1 is data, but we're going to do one step before that. And I'm just going to get rid of this so we have a bit more space. So we've got our data ready. We've turned it into tensors way back at the start. Then we build a model, and then we picked a loss function and an optimizer. We built a training loop. We trained our model. We made some predictions. We saw that they were better. We evaluated our model. We didn't use torch metrics, but we got visual. We saw our red dots starting to line up with the green dots. We haven't really improved through experimentation. We did a little bit of it though, as in we saw that if we trained our model for more epochs, we got better results. So you could argue that we have done a little bit of this, but there are other ways to experiment. We're going to cover those throughout the course. And then we saw how to save and reload a trained model. So we've been through this entire workflow, which is quite exciting actually. So now let's go back through it, but we're going to do it a bit quicker than what we've done before, because I believe you've got the skills to do so now. So let's start by importing PyTorch. So you could start the code from here if you wanted to, and matplotlib. And actually, if you want, you can pause this video and try to recode all of the steps that we've done by putting some headers here like data, and then build a model, and then train a model, save and load a model, whatever, and try to code it out yourself. If not, feel free to follow along with me and we'll do it together. So import torch, from torch import Oh, would help if I could spell torch. Import NN, because we've seen that we use NN quite a bit. And we're going to also import matplotlib because we like to make some plots, because we like to get visual. Visualize, visualize, visualize as PLT. And we're going to check our PyTorch version. That way we know if you're on an older version, some of the code might not work here, but if you're on a newer version, it should work. If it doesn't, let me know. There we go, 1.10. I'm using 1.10 for this. By the time you watch this video, there may be a later version out. And we're also let's create some device agnostic code. So create device agnostic code, because I think we're up to this step now. This means if we've got access to a GPU, our code will use it for potentially faster computing. If no GPU is available, the code will default to using CPU. We don't necessarily need to use a GPU for our particular problem that we're working on right now because it's a small model and it's a small data set, but it's good practice to write device agnostic code. So that means our code will use a GPU if it's available or a CPU by default if a GPU is not available. So set up device agnostic code. We're going to be using a similar setup to this throughout the entire course from now on. So that's why we're bringing it back. CUDA is available. So remember, CUDA is NVIDIA's programming framework for their GPUs, else use CPU. And we're going to print, what device are we using? Device. So what we might do is if we ran this, it should be just a CPU for now, right? Yours might be different to this if you've enabled a GPU, but let's change this over to use CUDA. And we can do that if you're using Google Colab. We can change the runtime type by selecting GPU here. And then I'm going to save this, but what's going to happen is it's going to restart the runtime. So we're going to lose all of the code that we've written above. How can we get it all back? Well, we can go run all. So this is going to run all of the cells above here. They should all work and it should be quite quick because our model and data aren't too big. And if it all worked, we should have CUDA as our device that we can use here. Wonderful. So the beauty of Google Colab is that they've given us access to a NVIDIA GPU. So thank you, Google Colab. Just once again, I'm paying for the paid version of Google Colab. You don't have to. The free version should give you access to a GPU, albeit it might not be as a later version as GPU as the pro versions give access to. But this will be more than enough for what we're about to recreate. So I feel like that's enough for this video. We've got some device agnostic code ready to go. And for the next few videos, we're going to be rebuilding this, except using device agnostic code. So give it a shot yourself. There's nothing in here that we haven't covered before. So I'll see you in the next video. Let's create some data. Welcome back. In the last video, we set up some device agnostic code and we got ready to start putting everything we've learned together. So now let's continue with that. We're going to recreate some data. Now we could just copy this code, but we're going to write it out together so we can have some practice creating a dummy data set. And we want to get to about this stage in this video. So we want to have some data that we can plot so that we can build a model to, once again, learn on the blue dots to predict the green dots. So we'll come down here, data. I'm going to get out of this as well so that we have a bit more room. Let's now create some data using the linear regression formula of y equals weight times features plus bias. And you may have heard this as y equals mx plus c or mx plus b or something like that, or you can substitute these for different names. Images, when I learned this in high school, it was y equals mx plus c. Yours might be slightly different. Yeah, bx plus a, that's what they use here. Whole bunch of different ways to name things, but they're all describing the same thing. So let's see this in code rather than formulaic examples. So we're going to create our weight, which is 0.7, and a bias, which is 0.3. These are the values we previously used. For a challenge, you could change these to 0.1 maybe, and 0.2. These could be whatever values you'd like to set them as. So weight and bias, the principle is going to be the same thing. We're going to try and build a model to estimate these values. So we're going to start at 0 and we're going to end at 1. So we can just create a straight line, and we're going to fill in those between 0 and 1 with a step of 0.02. And now we'll create the X and Y features, X and Y, which is features and labels actually. So X is our features and Y are our labels. X equals torch.arange, and X is a capital. Why is that? Because typically X is a feature matrix. Even though ours is just a vector now, we're going to unsqueeze this so we don't run into dimensionality issues later on. You can check this for yourself. Without unsqueeze, errors will pop up. And Y equals weight times X plus bias. You see how we're going a little bit faster now? This is sort of the pace that we're going to start going for things that we've already covered. If we haven't covered something, we'll slow down. But if we have covered something, I'm going to step it through. We're going to start speeding things up a little. So if we get some values here, wonderful. We've got some X values and they correlate to some Y values. We're going to try and use the training values of X to predict the training values of Y and subsequently for the test values. Oh, and speaking of training and test values, how about we split the data? So let's split the data. Split data. So we'll create the train split equals int 0.8. We're going to use 80%, which is where 0.8 comes from, for the length of X. So we use 80% of our samples for the training, which is a typical training and test split, 80-20, thereabouts. You could use like 70-30, you could use 90-10. It all depends on how much data you have. There's a lot of things in machine learning that are quite flexible. Train split, we're going to index on our data here so that we can create our splits. Google Colab auto-corrected my code in a non-helpful way just then. And we're going to do the opposite split for the testing data. Now let's have a look at the lengths of these. If my calculations are correct, we should have about 40 training samples and 10 testing samples. And again, this may change in the future. When you work with larger data sets, you might have 100,000 training samples and 20,000 testing samples. The ratio will often be quite similar. And then let's plot what's going on here. So plot the data and note if you don't have the plot predictions function loaded, this will error. So we can just run plot predictions here if we wanted to, and we'll pass it in xtrain, ytrain, xtest, ytest, and this should come up with our plot. Wonderful. So we've just recreated the data that we've been previously using. We've got blue dots to predict green dots. But if this function errors out because you've started the notebook from here, right, from this cell, and you've gone down from there, just remember, you'll just have to go up here and copy this function. We don't have to do it because we've run all the cells, but if you haven't run that cell previously, you could put it here and then run it, and we'll get the same outcome here. Wonderful. So, what's next? Well, if we go back to our workflow, we've just created some data. And have we turned it into tensors yet? I think it's just still, oh yeah, it is. It's tensors because we use PyTorch to create it. But now we're up to building or picking a model. So we've built a model previously. We did that back in build model. So you could refer to that code and try to build a model to fit the data that's going on here. So that's your challenge for the next video. So building a PyTorch linear model. And why do we call it linear? Because linear refers to a straight line. What's non-linear? Non-straight. So I'll see you in the next video. Give it a shot before we get there, but we're going to build a PyTorch linear model. Welcome back. We're going through some steps to recreate everything that we've done. In the last video, we created some dummy data, and we've got a straight line here. So now, by the workflow, we're up to building a model or picking a model. In our case, we're going to build one to suit our problem. So we've got some linear data, and I've put building a PyTorch linear model here. I issued you the challenge of giving it a go. You could do exactly the same steps that we've done in build model, but I'm going to be a little bit cheeky and introduce something new here, and that is the power of torch.nn. So let's see it. What we're going to do is we're going to create a linear model by subclassing nn.module, because why? A lot of PyTorch models subclass nn module. So class linear regression, what should we call this one? Linear regression model v2, how about that? And we'll subclass nn.module. So much similar code to what we've been writing so far, or when we first created our linear regression model. And then we're going to put the standard constructor code here, def init underscore underscore, and it's going to take as an argument self, and then we're going to call super dot another underscore init underscore underscore brackets. But we're going to, instead of, if you recall above, back in the build model section, we initialized these parameters ourselves. And I've been hinting at in the past, in videos we've seen before, that oftentimes you won't necessarily initialize the parameters yourself. You'll instead initialize layers that have the parameters inbuilt in those layers. We still have to create a forward method, but what we're going to see is how we can use a torch linear layer to do these steps for us. So let's write the code and then we'll step through it. So we'll go use nn.linear, because why? We're building a linear regression model and our data is linear, and in the past, our previous model has implemented the linear regression formula. So for creating the model parameters, so we can go self.linear layer equals, so this is constructing a variable that this class can use, self linear layer equals nn.linear. Remember, nn in PyTorch stands for neural network. And we have in features as one of the parameters and out features as another parameter. This means we want to take as input of size 1 and output of size 1. Where does that come from? Well, if we have a look at xtrain and ytrain, we have one value of x, maybe there's too many here, x5, we'll view the first 5. 5 and 5. So recall, we have one value of x equates to one value of y. So that means within this linear layer, we want to take as one feature, x, to output one feature, y. And we're using just one layer here. So the input and output shapes of your model, in features, out features, what data goes in and what data comes out, these values will be highly dependent on the data that you're working with. And we're going to see different data or different examples of input features and output features all throughout this course. So, but that is what's happening. We have one in feature to one out feature. Now, what's happening inside nn.linear? Let's have a look. Torch nn linear. We go to the documentation. Applies a linear transformation to the incoming data. Where have we seen this before? Y equals x, a, t plus b. Now they're using different letters, but we've got the same formula as, what's happening up here? We've got the same formula as our data. Weight times x plus bias. And then if we look up linear regression formula, once again, linear regression formula, we've got this formula here. Now, again, these letters can be replaced by whatever letters you like, but this linear layer is implementing the linear regression formula that we created in our model before. So it's essentially doing this part for us. And behind the scenes, the layer creates these parameters for us. So that's a big piece of the puzzle of PyTorch, is that, as I've said, you won't always be initializing the parameters of your model yourself. You'll generally initialize layers, and then you'll use those layers in some forward computation. So let's see how we could do that. So we've got a linear layer which takes us in features 1 and out features 1. What should we do now? Well, because we've subclassed nn.module, we need to override the forward method. So we need to tell our model what should it do as the forward computation. And in here, it's going to take itself as input, as well as x, which is conventional for the input data. And then we're just going to return here self.linear_layer x. Right? And actually, we might use some typing here to say that this should be a torch tensor, and it's also going to return a torch.tensor. That's using Python's type-ins. So this is just saying, hey, x should be a torch tensor, and I'm going to return you a torch tensor because I'm going to pass x through the linear layer, which is expecting one in feature and one out feature. And it's going to this linear transform. That's another word for it. Again, PyTorch and machine learning in general has many different names for the same thing. I would call this linear layer. I'm going to write here. Also called linear transform, probing layer, fully connected layer, dense layer, in TensorFlow. So a whole bunch of different names for the same thing, but they're all implementing a linear transform. They're all implementing a version of linear regression. Y equals X, A transpose plus B. In features, out features. Wonderful. So let's see this in action. So we're going to go set the manual seed so we can get reproducibility as well. Torch.manual seed. And we're going to set model 1 equals linear regression. This is model 1 because we've already got model 0, linear regression v2. And we're going to check model 1 and we're going to check its state dictionary. State dict. There we go. What do we have inside this? Ordered dict. Has that not created anything for us? Model 1 dot state dict. Ordered dict. We haven't got anything here. Linear regression model v2. Ideally, this should be outputting a weight and a bias. Yeah, variables, weight, and bias. Let's dig through our code line by line and see what we've got wrong. Did you notice this? The init function, so the constructor had the wrong amount of underscores, so it was never actually constructing this linear layer. Troubleshooting on the fly, team. There we go. Beautiful. So we have a linear layer, and we have, it is created for us inside a weight and a bias. So effectively, we've replaced the code we wrote above for build model, initializing a weight and bias parameter with the linear layer. And you might be wondering why the values are slightly different, even though we've used the manual seed. This goes behind the scenes of how PyTorch creates its different layers. It's probably using a different form of randomness to create different types of variables. So just keep that in mind. And to see this in action, we have a conversion here. So this is what's going on. We've converted, this is our original model class, linear regression. We initialized our model parameters here. We've got a weight and a bias, but instead we've swapped this in our linear regression model v2, this should be v2, to use linear layer. And then in the forward method, we had to write the formula manually here when we initialized the parameters manually, but because of the power of torch.nn, we have just passed it through the linear layer, which is going to perform some predefined forward computation in this layer. So this style of what's going on here is how you're going to see the majority of your PyTorch deep learning models created using pre-existing layers from the torch.nn module. So if we go back into torch.nn, we have a lot of different layers here. So we have convolutional layers, pooling layers, padding layers, normalization, recurrent, transformer, linear. We're using a linear layer, dropout, etc., etc. So for all of the common layers in deep learning, because that's what neural networks are, they're layers of different mathematical transformations, PyTorch has a lot of pre-built implementations. So that's a little bit of a sneaky trick that I've done to alter our model, but we've still got basically the exact same model as we had before. So what's next? Well, it's to train this model. So let's do that in the next video. Welcome back. So in the last video, we built a PyTorch linear model. nice and simple, using a single nn.linear layer with one in feature, one out feature, and we overrid the forward method of nn.module using the linear layer that we created up here. So what's going to happen is when we do the forward pass on our model, we're going to put some data in and it's going to go through this linear layer, which behind the scenes, as we saw with torch nn linear, behind the scenes it's going to perform the linear regression formula here. So y equals x, a, t plus b. But in our case, we've got weight and bias. So let's go back. It's now time to write some training code. But before we do, let's set the model to use the target device. And so in our case, we've got a device of CUDA, but because we've written device agnostic code, if we didn't have access to a CUDA device, a GPU, our default device would be a CPU. So let's check the model device. We can do that first up here. Check the model current device, because we're going to use the GPU here, or we're going to write device agnostic code. That's better to say. Device agnostic code, that's the proper terminology. Device, what device are we currently using? This is the CPU, right? So by default, the model will end up on the CPU, but if we set it to model1 call.2 device, what do you think it's going to do now? If our current target device is CUDA, we've seen what 2 does in the fundamentals section. 2 is going to send the model to the GPU memory. So now let's check where the parameters of our model live, .device. If we send them to the device, previously it was the CPU. It's going to take a little bit longer while the GPU gets fired up and PyTorch goes, hey, I'm about to send you this model. You ready for it? Boom, there we go, wonderful. So now our model is on the device, or the target device, which is CUDA. And if CUDA wasn't available, the target device would be CPU, so this would just come out just exactly how we've got it here. But with that being said, now let's get on to some training code. And this is the fun part. What do we have to do? We've already seen this. For training, we're just going to clear up our workspace a little bit here. For training, we need, this is part of the PyTorch workflow, we need a loss function. What does a loss function do? It measures how wrong our model is. We need an optimizer. We need a training loop and a testing loop. And the optimizer, what does that do? Well, it optimizes the parameters of our model. So in our case, model1.stateDict, what do we have? So we have some parameters here. Within the linear layer, we have a weight and we have a bias. The optimizer is going to optimize these random parameters so that they hopefully reduce the loss function, which, remember, the loss function measures how wrong our model is.